দেখিছিল না মানে হেৰি যে নাকি হাউচিং কলনী এইটো বহুত জায়গা খোজকাঢ়া মানে তাত একো ৰেষ্ট্ৰিকশ্যন নাই ভিতৰত সন্ধিয়া হলে গেট বন্ধ কৰি দিয়ে কেম্পাছৰ গোটেই কেম্পাছটো
Yeah, that is a nice place we have.
Dr. Barua? Arnab? Arnab? Arnab?
Oh, sir.
আমি আৰম্ভ কৰো না
হয় স্যার আমার গায়ত্রী আছে তাই আহি আছে Okay, Gayatri, are you there?
Yes, sir.
I think we should start. People will keep on joining, no problem. But we should keep to the time.
Yes, sir.
So I think you can start the procedure.
Okay, sir. Sure, sir. A very warm good morning to one and all present here. Myself, Gayatri Das, Assistant Professor, Civil Engineering Department, on behalf of Faculty of Engineering and Technology, welcomes you all to the opening ceremony of our International Faculty Development Program on Climate Change Challenges and Disaster Risk Reduction, organized by Faculty of Engineering and Technology, Assam Downtown University, which is going to held from today to 26th of July. We feel honored to have our Chief Patron as Dr. N.N. Dr. Sir, Chancellor, Assam Downtown University, our Patron, Professor N.C. Talukdar Sir, Vice Chancellor, Assam Downtown University, Professor Vandana Datta Ma'am, Dean of Studies, Assam Downtown University, and Chairperson Research, Professor Dharmeshwar Das Sir. Now, may I request the convener of our FDP, Dr. Arnab Bormudoy Sir, HOD, Faculty of Engineering and Technology, to deliver the inaugural speech. Sir, please.
Thank you, Gayatri. I hope I'm audible. Is it?
Yes, sir.
Yes.
You are audible.
Honorable Chancellor, Sir, of Assam Downtown University and our Chief Patron of our International FDP, Dr. Narendranath Datta, Honorable Vice Chancellor, Sir, and Patron of our FDP, Professor Narayan Chandra Talukdar, Honorable Dean of Studies and Patron of our FDP, Professor Vandana Datta, respected Chairperson of the FDP, Professor Sunandan Barua, respected Guest of Honor of the program, Professor Bhupendranath Goswami, respected Deans of various faculties, my dear colleagues, participants, and friends. A very good morning to every one of you today. On behalf of the FDP, I, Dr. Arnab Bormudoy, the convener, would like to formally welcome you all to this inaugural session. As you may be aware that only this week, more than 120 people have been killed and an equal number missing after the worst floods in the Western Europe in several decades. In Germany, emergency workers are still looking for dozens unaccounted for, and Chancellor Angela Merkel has described her experience of these floods as somewhat surreal. The floods in Germany are not the only extreme weather events we are witnessing this summer. There has been a dramatic heat wave in Canada and in Western US and Russia, Mexico and New Zealand. All have been experiencing unusually high temperatures. The climate science is very clear about all these. It has been predicting not only for years, but for decades that if we continue our pump of huge amounts of carbon dioxide into the atmosphere, we will experience more of such weather events and extreme events in the coming years. In front of us, there lies a grim reality. It concerns us the most. It's just the scale and urgency of the challenge. If we look at the current emission of carbon dioxide and its trend of increase, it needs not to put in a complete reversal. It needs to be put in a complete reversal if we need to avoid exceeding 1.5 degrees by 2030. For countries such as ours, it is a diabolical question how we would be able to balance the quest for an economically developed society, protecting the environment, and at the same time meeting the Paris Agreement goals. In terms of viewing natural disasters as not only a response-centric event, we as a nation have started to adopt a more holistic approach to the entire disaster risk reduction process since 2005, after the Hoo's earthquake and the Great Indian Ocean tsunami. In this journey of 16 years, we are trying to fit the new framework, and suddenly we are burdened with the additional uncertainty of climate change. We have made genuine and serious pledges as a country to change our habits of energy consumption and uplift a billion population to a level of climate awareness which were never imagined before. The challenges in front of us are huge, but so are our aspirations too. With this FDP, I want all the participants to remember this pledge and reassure oneself that in this fight for a global climate goal, we as Indians become responsible stakeholders and understand our duties and challenges that lie in front of us, so that we can be educators and at the same time we can teach or make aware another 10 people around us with our actions in this green background, and look for a possible measure for adaptation that will leave a lesser footprint of carbon dioxide in the existing cauldron of greenhouse gases. Let all the participants who are here in the FDP today be some agents of transformation and in due course set examples for a sustainable future. So with this, I would like to formally welcome you all, and then I hand over again to Gayatri. Thank you.
Thank you so much, sir. Now, may I kindly request Honorable Vice Chancellor Sir, Dr. N.C. Talukdar, to speak a few words. Sir, please.
Namaskar and very good morning to you all. Our invited guest and very respected Professor Bhupendranath Goswami. And I am not sure whether Chancellor Sir is attending or he has sent a message. But very good morning to you, sir, if you are here. Bandra Madam and all the other colleagues of Engineering and Technology faculty and all the eminent participants of this faculty development program. I welcome you from the Office of Vice Chancellor to this faculty development program organized in digital platform. Last 2 weeks, this university has been holding faculty development program end-to-end. Yesterday, the beginning of one in pharmaceutical science, and day before yesterday, 7 days duration program, faculty development program of humanities and social science ended. So it's kind of whether it is kind of a unwritten rule that in every meeting I have to speak few things, whereas I am not, I don't have knowledge in each and every discipline. And what I see, the Dr. Arnab Bormudoi during his welcome speech very nicely articulated the climate change issues and the problem and the sustainability of this planet. What I thought, I just share with you 4 slides. So in some occasion, I prepared these slides, and most of the things there is known, but there are some data. So I'd just like to share you 2-3 minutes it will take, if you permit.
Sure, sir, please.
Is it visible?
It's coming, yes, sir.
Okay.
Yes.
So I think these slides that human population increase, reduced arable land, biodiversity loss, and reduced access to safe drinking water. Like this is all is given rise to global ecosystem sustainability issue. In fact, it's linked with global climate change. a population of roughly 100 crores in 1803 has gone to 780 in latest data. In 2020 it is 780. Maybe it has gone, it's more than 780 crores now, because it's last year, I think in July, this data I collected. And if you look at about 65% of the animal and plant species between 1975 to 2020 gone from this planet. And we all know the problem, consequent problem. And we talk about methane gas emission, carbon dioxide, greenhouse gases effect, or blame our farm kettles for methane production, wetland of the world. But what about these 680 crores people? Like there are only 100, and now 680 crores people compared to 1803. How much carbon dioxide they're giving out? Next slide. It shows some like these are all known things. So the agricultural expansion of at the expense of the forest. Like we all know this contribution, forest cover has gone. There is not much sink of carbon dioxide and exaggerating the problem of climate change. And I have missed one very important slide. That was a slide which has documented decade-wise the extreme climate event. Like that, I think Dr. Goswami is going to show that slide. I saw in one of his presentation is going to show that. Let me just tell you another important aspect of what is happening, which is silently happening. That if you look at the history of agriculture, which started about 10,000 years ago, about 8,000 before Christ, the agriculture like was in a very primitive form. It's a very natural way it was happening, a balanced state. But with increase in population and the Green Revolution, the population increase, then corresponding increase in the consumption of pesticide, consumption of fertilizers, which contribute tremendous amount of nitrous oxide, UV, that UV layer, ozone depletion, UV penetration. We all know this. Now, what has happened actually? This modern agriculture, without knowing, we have reduced the microbial population of the soil system, and the microbial population being a huge amount of carbon dioxide. It's also a very big sink of carbon dioxide, and their population loss has given rise to, with other factor, loss in carbon dioxide in the soil. And and it's a chain reaction, because high temperature again cause more decomposition. Already organic matter has depleted, and because of high temperature, more decomposition and more carbon dioxide release. Now this goes unnoticed, that how microorganisms contribute even in bringing like large quantity of carbon dioxide. And the last slide is it's a paper in Nature by Tillman. You see the global food production from 1960 was 0.8 into 10 to the power 9 megatons, which has gone to in 2019 to 2.7 into 10 to the power 9 megatons. And the fertilizer consumption in 1960, it was like about 10 into 10 to the power 6 tons. And today, like not today, in 2019 data, it has gone to 190. How many times? 19 times increase. Pesticide use in 1940 was almost nil. 1945, during World War II, DDT was the first insecticide used to repel insects for for the army who like had to go to forest for fight to like overcome the problem of pest. Like DDT first came out, and then it was when its pesticidal properties were known, it becomes a very important pesticide for agriculture. Since 1945, DDT of course now banned, but still in 2019, this many 3 into 10 tons of pesticide used in the world. Now, these 4 slides, what I have shown, has contributed towards or created an environment of greenhouse gas generation, which is the main cause of climate change. And we all there has been global efforts now. There have been several treaties, the heads of countries, a lot of measures they have brought to contain carbon dioxide emission. They have put target. So there's a global effort to contain this issue problem. But while that's a policy issue discussion at global level, but whatever action happens, it happens on a local level. Now, this kind of FTV, like FDP, like faculty development program, and maybe 100 or 120 participants will join. What will be important for each one of you to think what we can do locally. We see so many problems. It's flood problems of Europe, different country, Belgium, Germany. Like only last week we have seen the problem in Bombay, and then about 15-20 days there's another with those cyclone. There was another problem. Now we have been seeing this. Back home here, you see after a heavy shower, like what happens to Guwahati, some part of the Guwahati city. Now, when this city was built, maybe 70, 80 years ago, they could not foresee this climate change issue. Now you get rainfall earlier. The rain we used to get in a week, we get it in maybe one day in 3-4 hours. And then our drainage system is not trained to regulate that much water. And this is a city interspersed with hills, and those places which are just near the hillocks, they get inundated first. Now, we need to generate data. What is happening? How much water get discharged, get accumulated? How it drain out? These are small data. And Northeast being a mountainous region, about 65% of the land mass is mountainous, and these extreme rainfall event cause erosion at much faster rate. I just want to tell you that common people even are, without knowing what the in-depth problem of climate change and what is happening globally, without their knowing, they adopt some methods. They are inborn innovative. I just want to give you one example. In Nagaland, where Zoom practice is done, Zoom practice, you cut forest in a particular plot and burn the forest, and then you dibble seeds using a pointed or sharp material. You put a small hole and dig seeds. So in one of my visits to Nagaland, I learned from a farmer that nowadays he put seeds much deeper than before. I said, why you are doing this? He said, no, nowadays rainfall come like in short time, so heavy rainfall, then the seeds is washed away if I keep it on the surface. See the innovation a simple farmer is doing, right? So it is important what kind of innovations are happening at the grassroots. And it is important at a research scale at the level of intellectuals, group discussion and then brainstorming, and the issues that every year we are beginning to face, and what little research contribution, technology development we can do to mitigate these problems. I think very important thing, and I believe that this kind of faculty development program takes care of this requirement of work, research, innovation at the local level, and sensitize those young people, researchers who have been who will be attending this. With these words, thank you very much for asking me to share a few thoughts. And I wish that this 7 days faculty development program will be very successful and will be able to generate some technology innovation for solution of problems of climate change at local level. Thank you very much.
Thank you so much, sir.
Thank you so much, sir. Thank you so much, sir, for this quick, wonderful presentation. Now, may I kindly request Honorable Chancellor Dr. N. Dutta, sir, to kindly speak a few words. Though he is not physically present in this meeting, but he has wished us good luck for this FDP and has shared a video for all of us. May I request our IT department, to kindly play the video.
Voice is not coming.
অংকুৰ ভইচটো অহা নাই
Hmm.
অংকুৰ অডিও ট্ৰেক কিবা এটা অসুবিধা হৈছে
The voice is not there. You can't hear. Ankur has to take care, no? Because this is a recorded video, so.
Thank you very much, Gayatri. Am I audible? Can you confirm?
Yes, sir, you are audible.
Okay. So, Professor Bhupendranath Goswami, esteemed guest of honor and keynote speaker for today, Professor N.C. Talukdar, sir, Honorable Vice Chancellor, Professor Dharmeshwar Das, sir, Chairperson Research, all distinguished guests, participants, and faculty members of Engineering and Technology, a warm welcome to all of you from my side. Today, when I was going through the registrations, I found that this has actually become a real international program in the real sense of the term. So among our honorable speakers and resource persons, we have experts from 4 different countries: India, Japan, Thailand, and Switzerland. And among the participants today, I noticed participants from 6 countries: India, Pakistan, USA, Oman, Australia, and Sweden. So it's a warm welcome to everyone from different parts of the globe. Now it gives me immense pleasure to introduce the speaker for today, our keynote speaker and guest of honor, Professor Bhupendranath Goswami, sir. Well, there's so much to tell about him, but I have kept the introduction very concise so that we can proceed with his lecture. Professor Goswami is a renowned Indian meteorologist, climatologist, a former director of the Indian Institute of Tropical Meteorology, and a Pisaroti Chair Professor at the Indian Institute of Science, Education, and Research. He is currently a Serb Distinguished Fellow at Cotton University, Guwahati. He is known for his researches on the Indian monsoon dynamics and is an elected fellow of all the 3 major Indian science academies, that is the Indian National Science Academy, Indian Academy of Sciences, and the National Academy of Sciences India, as well as the World Academy of Sciences. The Council of Scientific and Industrial Research, the apex agency of the Government of India for Scientific Research, awarded Professor Goswami the Santi Swarup Bhatnagar Prize for Science and Technology, one of the highest Indian science awards, for his contribution to Earth, atmosphere, ocean, and planetary sciences in 1995. We all recall the wonderful interaction we had when Professor Goswami delivered the 2nd lecture in the Chancellor's Lecture Series of our university, and it was such a profound and very, very interesting talk that he delivered, and we look forward to another wonderful talk from him today. So without much ado, I would like to request Professor Goswami, sir, to kindly start his lecture. Over to you, sir.
Thank you, Professor Borua. Good morning to all of you, Professor Talukdar, Professor Arnab Formudai, and all the participants. it is my pleasure to be here today. And Professor Talukdar has already given a little glimpse of what I may be talking. So my idea is to sensitize you to the seriousness of this problem. And this problem is essentially as Dr. Talukdar mentioned, the problem is essentially due to the degradation of our environment by the population, by the humans, the increasing population. Is this screen visible now? Hello.
Yeah, screen is visible. Yeah.
Okay.
You can even go to slideshow mode also.
The slideshow mode doesn't work. We tested that before.
Okay.
So I think
but still very clear.
Okay,
very clear. Yeah. Otherwise also very clear.
Okay. So what I'm going to do is that I want to just highlight that today our Earth, which is a very unique place in the universe where the climate and everything else, the environment is just the right for sustaining life and nurturing it. But due to the overexploitation of the resources as well as the degradation of the environment, we humans have caused so much damage to this environment as well as the atmosphere that this Earth is today crying out loud that that it cannot sustain it anymore, and unless we do something very serious, then it will be very difficult that to sustain the human population itself. So, and that is why I would talk about basically what is climate change, and we'll give a very brief introduction to the science of climate change. Of course, many of you are already aware of the different disasters that are increasing threat of different disasters. I'll give a few examples. Of course, our interest is primarily to how the regionally Indian monsoon, in particular, even in our Northeast India, climate is being affected by this climate change, is of interest to us because we need to develop a adaptation strategy and possible mitigation strategy towards these. And therefore, I will talk about a little bit on those climate change. Some of the work that we have done on Indian monsoon, climate change, on effect of climate change on Indian monsoon in general, and Northeast India climate in particular. So then I shall talk a little bit about a couple of issues that are of interest in Northeast India and what we might need to do in terms of disaster risk mitigation and also in terms of adaptation to these effect of climate change on the Northeast. Finally, I would like to talk about how all this we have landed up in a big mess today. Art has evolved over the last 4.6 billion years, but due to the activity of human being over the last 200 years, now we are at a stage of almost no return, which is threatening the existence of the human being itself. So we should recognize those why this has happened, and then only we'll be able to take other mitigating policies. And so to show the seriousness of this problem, I will talk about how the degradation of the environment has grown, as Dr. Talukdar has mentioned slightly on this issue, and I will elaborate on that part of this. And finally, I'll talk about a sort of what is my take on all this. So climate change, as you know, climate change can be a sort of can be demonstrated by just one parameter. Is the global mean temperature increase over the last 1,000 years. So if you look at the evolution of the sort of temperature change over the last 1,000 years, it appears that over the last 200 years, there is a major change. And this data has been now collected over a large number of sources and validated. There has been a time when this data, there are certain issues, certain questions, but I don't think there is any more. There is issues. The change of global mean temperature of about almost 1 degree over the last 100 years there is no question about that. And this is what is causing. It may look like the 1 degree change is not big, but as I will illustrate, that this 1 degree change over 100 years is very big. And that is what is responsible for creating the climate, taking the climate to a stage where it may be very difficult to bring it back. And this is what the global warming is. And of course, the cause of this is essentially due to the greenhouse gases. And two main greenhouse gases are, of course, carbon dioxide and methane. And then, of course, there are some few minors. I'm not going to go into details. And the observations of these over the last 50, 60, or 70 years, where there is very good observations, has clearly shown that this data is in the atmosphere, the concentration of carbon dioxide as well as methane is increasing very rapidly. Today, the level of carbon dioxide in the atmosphere is about 414 parts per million, while the methane is about 1855 parts per billion. So these are kind of just, I want to give you, give these two numbers just to remember that, and then because we will try to look at in the context of how carbon dioxide and global and methane has changed in the past. So to look at that, so to put that to the current level of greenhouse gases in the context of how the carbon dioxide and methane changed over the last 1 million years, for example, these are data collected from the Antarctic ice core, which has been dug for almost about 4 kilometers and analyzed, looked, dated, and taking air bubbles from inside the ice, you can measure the carbon dioxide and methane concentration, as well as from the oxygen isotope changes. You can measure delta and deuterium changes can give you the idea of the ice volume change. Oxygen isotope changes can give you the idea of the temperature change, and those analysis has given us a chronology of how temperature has changed over this almost 1 million years, and how carbon dioxide and the methane also changed. Interesting thing to note is that over this period, there are about 8 what you call now ice age cycles, or the glacial interglacial cycles. So one of them is the glacials, and these are the interglacial period. This is interglacial period. These and these are glacial periods, and these are about 8 cycles have gone. And over these 8 cycles of large climate variability, the level of maximum carbon dioxide in the atmosphere is never more than 280 parts per billion. And today it is, as I said, that is why I wanted you to have that number, 414 or 18 parts per million. And similarly, the methane was like 400 to 700 parts per billion, but today it is 855 parts per billion. So there is a huge change from this over the last 1 million compared to what the level of carbon dioxide was in the last 1 million years. So this is a red flag that we should remember. Now, how did it come about, and sort of who is responsible for this? And this, of course, has the carbon dioxide is a inert gas. So once you it comes from fossil fuel burning all over the world, but different people, different countries have contributed differently over the years. And this is a sort of illustration how different countries over the last 100 years have added carbon dioxide into. Once the carbon dioxide is put in the atmosphere, part of it gets absorbed by ocean and the land and the vegetation over the land, and the rest gets to the atmosphere. And about 50% of what is emitted almost is actually left in the atmosphere. Now that keeps building up because carbon dioxide is a very inert gas. It doesn't react and gets destroyed. And so over 100 years, slowly they build up, and that building up affects the radiative balance and then affects the climate. And this building up has happened by different people at different levels. For example, this is in China. China started late after 50s, but they rapidly grew, and today they contribute about 27% of the total. This is the kind of total contribution by all different countries. So it has gone from about 1.9 gigatons in 1900 to about 36.8 gigatons. So about 20 times has increased, or 25 times it has increased over this period. And that contribution has come from different countries in a different ways. China, you can see, the United States, you can see is that they started quite early because their industrial revolution started early. They started contributing more carbon dioxide early on, and by 1950s, they already put up a lot of carbon dioxide in the atmosphere. After that, they have started also still putting up quite a lot, although the rate has not increased as much as the rate China and other countries in the recent past, because industrialization and the expansion of economy has started late in these countries. The European Union is similar. They started early, they contributed significantly. So over these countries, the industrialized countries like the United States and the European Union, they have been contributing over 100 years. But the developing countries have started contributing only from about 1950s, 60s, and so on. India contributes that much, about 7% today. We started pretty late. In fact, until 1980s, our contribution was very small. Then our industrialization have started increasing, and that is contributing. We are contributing significantly today. We need to consider. But as far as per capita is concerned, our population is very large, and therefore, as per capita, we are still contributing less. But that does not mean that we should not do anything about it. We must do and contribute. So the others, you can be surprised. Russia is contributing also considerably today, and the other countries, and so on. So these are definitely causing all kinds of disasters, as mentioned in the opening remarks by the organizer today, very nicely. And locally, we can see that over the last few years, the hydrological disasters have started increasing. Because I cannot make this full screen, I had several pictures here, but forget about that. What has happened is, one of the things that has happened is that extreme events are increasing. As a result, hydrological disasters, flash floods, the landslides, flash floods, urban floods, these are definitely increasing, and increasing rapidly. Their frequencies are increasing, their intensity is also increasing. They are becoming more vigorous. At the same time, they are becoming more frequent. So this is one of the major problems that is being faced all over the world, including in our place. In addition to that, the heat waves have started increasing. So it is the heat waves are actually causing more death than the other things, even floods, because a lot of people, and it affects the human and livestock death. It also affects the crop loss. So it is affecting a lot of things, and therefore they are also very important. In addition, forest fires are also increasing because of the increased temperature. Certain parts become very dry at certain seasons, and then there is even a small spark will start increasing, setting up fires. And though the increasing forest fires, the frequency of forest fires have also started increasing. Necessarily, always there are some forest fires, but the frequencies have increasing. It produces biodiversity loss. It puts more carbon dioxide in the atmosphere. But in addition to that, what we are having, the disasters are taking place over other regions, like the permafrost regions, the regions where the ice is over land, it remains frozen. Those areas, the temperature over the extratropics are increasing at a rate which is higher than the temperatures over the in these other tropics. The regions, permafrost region temperature is increasing. As a result, some parts of permafrost are melting. When they melt, the biomass which is embedded there get exposed. They decay, and when they decay, they produce more methane in the atmosphere. And and because they are in a very dry regions, and lot of these and increase in temperature and the dryness in this region can lead to fires in the permafrost. I will give some examples of that later on. Of course, the tropical cyclone intensities are increasing, and therefore that gives rise to loss of life and property and livestock. And of course, sea level is increasing, because sea level increase depends on largely on not the sea ice, but on the land ice. Greenland and Antarctica, parts of Greenland and Antarctica are melting, and that water then adds to the sea level rise. And as a result, about 50 centimeter rise has taken place over the last 100 years. And it is expected that maybe another 50 centimeters or 1 meter rise will take place by the end of the century. And as a result of that, many atolls are vanishing, because these islands where almost the height is close to the sea level, so they tends to get completely submerged. But of course, coastal inundation will increase and increasing. And as a result, when the tropical cyclone hits this coast, because sea level has increased by 50 centimeter, that 50 centimeter increase can create the storm surge effect to have become much more intense. So as a result, the inundation to the land also will sufficiently increase significantly. So all these are causing biodiversity loss, and of course extinction of a lot of species, including human loss. So this is resulting in what we call the sixth mass extinction. I'll come back to that at the end of the talk a little bit. So some of the disasters, as you know, the Arctic Sea sea extent is decreasing every year, and that is causing a lot of biodiversity loss in those regions, as well as and this is the amount of, these are sort of research data from, and now today we can measure this from the sort of satellite monitoring, and can measure this loss very accurately. And this, in the recent years, this loss has accelerated significantly. And this is one of the where the sort of, now forest fires can be also measured from these from satellite today. And these are showing the kind of forest fires that are happening in Siberia in the recent years. So these are all increasing effect of. Last year, you have probably somebody has mentioned, and in Siberia there is a huge heat wave. This Siberia, the temperature at 70 degrees, your mean temperature is like 38 degrees, and it persisted for all, almost a month and longer. And as a result of that, obviously there will be fires, and those fires can be seen. And then not only as I said, the peatlands are those permafrost regions. So the peatlands also started getting fires, and that is, all this is putting more carbon dioxide into the atmosphere. And there is the storage of carbon dioxide is about 2 to 3 times larger than what has already been put there. And if this happens over the next few years, like even in the next 10 or 20 years, it will be disastrous consequence for the greenhouse effect, because greenhouse effect then will be so strong, there will be very difficult to revert it back with all the measures that we are proposing. Even recently, as the introductory remarks mentioned, there was a huge heat wave in the northwestern North America, and in this is a picture of June 27th. The maximum temperature here is above climatological mean values by more than 15-20 degrees, and during June and July 20, the highest temperature ever measured in Canada was like 49-50 degrees at about 50 to 60 degrees latitude. So this is like unprecedented, and these are causing lot of effects on this. This is an example of that. Lytton, British Columbia, this temperature is almost like 50 degrees. And that is a latitude of 50 degrees. You can imagine this mean climatological mean temperature in summer here will be like 30 degrees at the most, not even 30 degrees. And then and these are causing some interesting phenomena, which is these are called pyrocumulonimbus. So it produces, this extreme heat produces fire produces smoke, and this is so hot that the smoke and the smoke rises very rapidly to the upper atmosphere, and whatever little moisture is there, it gets condensed at very high level that produce ice crystals here. This is what are they called pyrocumulonimbus. And there is beautiful pictures from, this is a Lancet picture of June 30th, and there is beautiful picture how these are evolving, and they have also has a feedback effect into these maintaining these fires and the heat over this region. So it's a very sort of a new phenomena, and are being seen because of these extreme heat waves. And this has been happening because this is happening because together with the surface warming, there was a certain large-scale circulation has produced a high pressure at the top. This high pressure has sort of produced a heat dome, and this was not allowing heat to ventilate. And as a result, the heat actually built up, and became very, very hot. But a part of climate variability or the weather variability, or is it because of climate change? Now there is a lot of studies which use what is called attribution studies. Now attribution studies uses models and past data over last 200 years or whatever observations that we have. And based on these studies, it is now concluded that these events could have the chances of such events happening has increased by 150 times in the recent years because of the whole change in the environment and the climate change. The increase of global mean temperature has made these events to be much more likely, so much more that it's almost certain that these events have happened due to climate change. So, and there is a lot of studies now, and most of the events like the floods that I mentioned can also be attributed to climate change today. 5 years ago, before that, I would not have vouched it that it is because we did not have enough studies. But today, I think we have a lot of studies which the attribution and can be made with a high probability. So let me talk briefly on the science of the climate. Science of the climate change is, of course, is essentially due to the radiative balance. So the Earth gets radiation from the sun, and the part of it gets reflected by the surface and the clouds. That is, so the certain amount of solar energy comes per unit area. The Earth being a spherical, almost spherical object, so it intercepts pi r square area, and so this much energy per unit area, and this fraction is reflected. So 1 minus alpha into s, pi r square is the amount of solar radiation that comes in, and the Earth is a black body. It radiates like a black body, and it radiates proportional to the T to the power 4 with a Planck's constant over the whole globe, 4 pi r square. So this radiated energy, if it gets lost to the space, and whatever radiated energy gets lost to the space is balanced by how much is received from the sun, incoming solar radiation. That determines what should be the main temperature of the surface of the Earth or the atmosphere above it. So, so this is a very simple radiative balance. So it is determined by how much is reflected back and how much is this parameter is what is called infrared infrared the fraction of the solar long wave radiation. The Earth actually radiates at a long wave because of its mean temperature being at about 300 degrees Kelvin, whereas the sun's temperature is about 6000 degrees Kelvin. Its maximum energy comes in the short wave, but short wave, whereas Earth radiates in the long wave around 12 micron. So a part of that that long wave gets absorbed in the atmosphere because of the certain gases in the atmosphere provides has an absorption band in the long wave region, and they absorb that. As a result, that much energy is not allowed to go out, and it hits up the atmosphere. And as a result of that, only a fraction of the long wave radiation emitted gets escaped to the space, and that transmissivity factor is less than 1, and so that factor is represented by this. And this depends on the atmospheric constituents. Depending on what kind of atmosphere is there, carbon dioxide and water vapor are two major absorbers, including methane, of the long wave radiation, and that is what produces what is our greenhouse effect. And that, so it depends on the environment. So this particular long wave infrared transmissivity depends on the environment. So these are two things, and this also depends on the environment, the ocean atmosphere distribution. Ocean has different reflectivity, land has different reflectivity, trees have different reflectivity. So the average reflectivity of the solar radiation depends on the environment, the distribution of the land, the ocean, trees, etc. So these two things, if we disturb, they will disturb the balance, and that is what is happening today. And I'll just so you can actually calculate what the temperature would be by equating these two. And if there is no atmosphere, and suppose my infrared transmissivity was just 1, that means there is no atmosphere. Whatever is radiated, it goes to the space, and then you balance. You will get a mean temperature of the Earth, which will be minus 18 degrees Celsius, and it will be an ice-covered Earth, and no life will be possible. So we have a natural greenhouse effect because the atmosphere has certain amount of carbon dioxide and water vapor, and that provides a natural greenhouse effect, which makes the Earth livable, and this and it increases the mean temperature by about 33 degrees. So this is the crux of the problem. So we have to maintain this balance, and if we increase the carbon dioxide in the atmosphere, what is happening is that it is absorbing more long-wave radiation, therefore not letting that much go out. Therefore, you have to increase the temperature of this atmosphere to make the equal amount to go out to space. So as a result, the temperature will increase. And that is what is happening today. So this can explain the temperatures of in all our planets, depending on what is their constituent of the atmosphere, and how far it is from how much solar radiation they give, what is the reflectivity. If I know, I can actually calculate their mean temperature, surface temperature. So, but this is not that simple to calculate exactly how much temperature increase will take place. Will depend on a lot of internal processes in the ocean atmosphere system. As a result, it is not trivial to calculate the global mean temperature increase by that simple relationship that I mentioned. So it involves clouds in the atmosphere and especially the clouds make a major problem in calculating things, because we have these multiple scales involved in cloud calculating how much, what is the organization of the cloud, and how much the clouds do two things. One is, of course, it will reflect some of the solar radiation, but it also heats up the atmosphere because it releases latent heat energy. And that latent heat depends on the distribution of the cloud and the type of the cloud. So we need to calculate the heating from the clouds and the reflectivity of the clouds by actually simulating the distribution of the clouds properly. And that is a very challenging problem because it depends on a very large range of scales. Because it starts with the formation of the cloud condensation nuclei, which is at a very micron scale size, to cloud droplets of a millimeter size, which then organize into make individual clouds of a kilometer size. Then disturbances like tropical cyclones of 500 kilometer size, which again gets organized into a large scale cloudy pattern, which is called intertropical convergence zone of 10,000 kilometer size. So this ranges a 15 order of magnitude scales. And how do we model them? This modeling is non-trivial, is very difficult, and this is actually a very, very challenging problem. And that is where we have certain uncertainty, and that makes it difficult to completely accurately, exactly give how much temperature change will take place, and that uncertainty we will have to estimate. We can now estimate that uncertainty, but the other uncertainty also comes from other feedbacks that is there within the system. For example, the clouds can different clouds have different radiative effect. One is the low level clouds. Low level clouds will absorb more long wave radiation and reflect. So let a small amount of long wave radiation it lets out. But high level cloud, again, not being able to make this full screen has a little sometimes difficulty. Okay, so the high level clouds are more transparent to long wave, short wave radiation, so more short wave radiation come in, but high clouds trap more heat, and the low clouds trap less heat and reflects more heat, more solar radiation. So therefore, depending on the distribution of low clouds of the high clouds, you have a different feedback. Then the water vapor also has two different possible feedbacks. And normally, water vapor has a greenhouse effect. So it will, if the carbon dioxide increases the temperature, the atmosphere, there will be more water vapor, because increasing the temperature will have a larger water holding capacity of the atmosphere, more moisture in the atmosphere. More moisture in the atmosphere will lead to more greenhouse effect, but more greenhouse effect will add to the carbon dioxide greenhouse. So it is a positive feedback. So in increasing global temperature by carbon dioxide can trigger in a positive feedback and increase it further through greenhouse effect of the water vapor. But water vapor has other indirect effect. Water vapor produces more low-level clouds, and then it could reflect more. If water vapor produces more greenhouse, more low-level clouds, then it will reflect more solar energy. So the albedo will increase. If the albedo increases, the surface will cool, and therefore it can have a negative feedback. So in practice, both of these things will be happening. Now, which one will take? Which one will gain over the other is not known exactly, because that even from observations we don't know what is actually is, and then modeling we have to balance that correctly, and that is a very challenging task. So these are some of the issues, that complexities. There are many other complexities. I cannot go into details, but the complexities of the system is such that it is very difficult to quantify it exactly, given a number. But we can do a lot of studies and modeling studies and give a probability. And the models have improved today to the extent that we can actually say what is most probable, and that is very, very encouraging. And that is something that we can give. And so and most of this confidence that we have today in terms of the global warming effect on the on various different things on the earth is based on the fact that we have much more confidence in the probability of some of these things happening today. And that is what is the most important thing. And so we need to be very concerned about the effect of the global warming, because, as I mentioned, there is a potential things that is going to add to a positive feedback of the greenhouse gases, and this positive feedback then can take us to a runaway greenhouse effect. And this is something called going beyond the tipping point. This climate system has tipping points, and these tipping points, if I go, the equilibrium climate goes to a point beyond the limit, then the whole new climate system it lands up in a whole new different climate system, which can be completely different from what we live in, and that may have a disastrous effect on the ecosystem, the human, and everything. So to illustrate that, this is an example of very simple example of this sea level rise over the last 1 million years, as I mentioned, from those what you call the Antarctic ice core. Then we have the ice volume record from delta oxygen, delta deuterium records, and the ice volume can be used in a model to give us what is the sea level, what will be sea level. So sea level variations we can get. We can also get sea level variations are given here, and then we have temperature variation. So if I plot the temperature variations over the glacial, interglacial periods and the sea level variation. So glacial period sea level goes down drastically by about 150 150 meters, almost more than 100 meters, and then it comes back to interglacial period, which is normal or slightly above normal, and then and that is what is going on over the last 8 cycles. Temperature have changed, but today our temperature is here slightly above the past interglacial periods maxima. It is already slightly above of the past known interglacial periods. So we are in a very, very critical juncture. Now, if we do a lot of steps to completely curb this list of greenhouse gas increase in the atmosphere, we have to take a huge step, and then only it may be possible to bring it back. It will continue to rise because today the temperature already there is a whole lot of carbon dioxide in the atmosphere, and they are going to remain there for 100 years. Unless we do something, mean temperature is going to rise. In the next 50 years, it will continue to rise. Question is, can we stop at some point? Even if you stop at 50 to 100 years from today, I have to take measures today. And unless we do that, we will not be able to. Suppose we do all that measures, maybe after 100 years, 50 years, I will be able to bring it down. And then maybe we will remain within this loop. Why this is important, I'll show you in a minute. Towards the end, I'll show that the present temperature, the mean temperature of the climate is very important for these feedbacks that produces glacial interglaciation, and keeps it in a sort of stable equilibrium. Although glacial interglaciation are large swings, the mean temperature has not changed. The overall, suppose the mean temperature has not changed very. In the last, if you look at 65 million years of history, Earth has cooled slowly. I'll show that in a minute. But then over the last 3 million years, the mean temperature has remained more or less the same, and although with large fluctuations. But it is possible that today we can go out of that bound and go to a climate which may be before 3 million years ago, much before, much different climate. And that is the major concern. So that is why we need to do this. And these are some of the points in the history about evolution, this is A is mid Holocene. This is mid Holocene. We are in the late Holocene. Then this is Permian. Then mid Pliocene. C is mid Pliocene. D is mid Miocene, and so on. So there are different stages of historical evolution of the Earth. Those are the temperatures where somewhere they are, and obviously there is no this kind of feedback that was possible, because the mean temperature is very, very important, and that is where this tipping point comes in. So Indian monsoon, so we did a lot of studies. I think I have to move faster a little bit, but what I'll show is that Indian monsoon, we have found that Indian monsoon is generally stable relatively over the last 200 years, as I know. But it has a very small increasing trend. This is the rainfall of India, average rainfall, departure from mean and normalized by its own standard deviation. So it is a normalized rainfall variations. And it has a multi-decadal variability, but trend is very weak. And we have found out by using a nonlinear model decomposition technique, and that there is a small nonlinear trend. This trend is about 3% increase of the mean by every increase in the global mean temperature. So that is, although small, is notable and is consistent with other changes in the globally. That mean temperature, mean rainfall increases rather slowly. Although the temperature is by the total amount of moisture in the atmosphere increases by about 7% with per degree increase of global mean temperature, the rainfall does not increase because of the dynamics and because of various other things. The rainfall, total amount of rainfall increases slower than that, and that is also happens in the monsoon. So monsoon is expected to increase slightly with this 3% increase in so 100 years, about 3% increase has taken place. But more importantly, what has happened is the extreme events, the rainfall, daily extremes, events that are more than 99% percentile, those events have increased significantly. In fact, they have increased over the last 50 years only. They have increased almost 2 times. In fact, last 100 years, they have increased about 3 times. So that is the measure. So although the mean rainfall does not increase very rapidly, but because the extreme events are local in nature, in terms of local small scale instabilities, the moisture content increase is directly proportional to the increase in the intensity of the local extreme events. Even though the mean rainfall, monsoon rainfall, is a large scale quantity, and that large scale quantity does not necessarily increase the total increase the local moisture content, because it depends on the large scale convergence rather than the moisture availability in a grid point. So it is consistent, but it is also very important. And then what has happened is that we estimated that, and how much does it increase? So estimation is that these increase over the last 100 years, for per degree increase of global mean temperature, the frequency of occurrence of the very heavy, very extreme events, the 99.9 percentile events, have increased 3 times more. The 99% increases, they have increased by about 2 times. So these, in other words, very extreme events have increased very significantly, and their intensity. Now, not only the number, their intensity also have increased by about 21% per degree. So over the last 100 years, their intensity have increased by about 21%, 22%. So that they are becoming more stronger. So they are becoming more furious. At the same time, they are becoming more frequent. So these 2 things combined is a deadly combination, or producing plus floods, and these urban floods and all the landslides and things like that. And this is what is happening. So I will not go into great details of these consequences, because that is quite apparent. This we have done also for the North Indian region. North Indian region, we have shown that similar thing happened. But North India, there is an interesting thing. The mean rainfall is decreasing rather than increasing in the central India or the all India level. So in the local region, our mean rainfall is actually decreasing. And these, again, decreasing almost at about 3% per degree. Okay. But extreme rainfalls are increasing. They are increasing at the rate of not 3 times, but about 50%, not very as fast as in the central India, but still increasing about 50% over the last 100 years. And their intensity is still increasing about 12.5%. So in the Northeast India, the situation is a little different, and is that mean rainfall is decreasing, but their frequency of occurrence of the extreme events as well as their intensity are increasing. So therefore, we are in a more precarious conditions, and so the floods and everything will be still. This small decrease in the rainfall is not going to decrease the level of our flooding, mean level of the Brahmaputra very much, but this increase in the frequency of occurrence and occurrence of the extreme events are going to produce the floods more frequent. And because of other things like silting and other things, the inundation and frequency of flood events also have increased. So in addition to this global warming, other land use, land cover effects in our region has added to this problem. So therefore, we are actually in a double. We have in double disadvantage in this. So we have to be more careful. So this is basically what we need to. These 2 things both can affect. So we have to use. I will not get into this. We have to adapt to this. The floods are going to be part of us. It is not going to go away and going to increase in the past. So in the Northeast, we have to adapt. We have to have an adaptation strategy. How can we live with this flood? And there is a potential thing. The floods are very common here. We know that, and it is very also very. It's a large scale, and the Brahmaputra, which is tributaries, are challenging. There's more rainfall. The topography is very different, and therefore it has its own influence on these floods. And so there are many challenges. We need more data in this, and what we need, I'll come back to that in the end. That this can be modeled. This can be there is good methodology, and data is also sufficiently good enough, and we can actually model this and there is expertise in this region. I don't think there is any problem, but we need to do it properly, scientifically. What I feel is that over the present time, it has not been, the operational flood forecasting has not been scientific, and we need to do it more carefully. And I have a prescription for that, which I'm not going to great details at this time. So there is also this, our biodiversity is also affected by these global warming, and Northeast region is a biodiversity hotspot, and this Northeast biodiversity in this region also has a very important impact on the sustainable development in this region, because many of our people depend on the biodiversity services, and there is a but the impact of this climate change, what will happen to many of this biodiversity as a result of the climate change and the extreme events increase is not quite known, and I have not seen good studies and quantification of this, and that is something that is very much important. This is something that we need from scientific side. So without getting into that very much, let me now come back to that. The last part of this is that we should be concerned because as Dr. Talgar mentioned in the beginning, that it is seriously affecting the biodiversity around the globe and species loss, and what is now known as 6 mass extinction. This is certainly happening. There are about 5 mass extinctions in the past, over the last 6, I mean, these about last 1 billion years, there are about 6 mass extinctions, and they're all due to different natural causes. But today we are having the mass extinction can be very much linked with the population growth, and that is what I'm going to do in the next few minutes, just to show you that all this degradation of the environment due to humans. So this mass extinction is measured by this species loss, and there is different way the paleontologist and the geologist and paleontologist and the climate scientists together, they find out from various records. There is a level of how much there is a certain amount of species die, certain new species evolve. There is a background level of species that loss that keeps taking place. But it turns out that in the recent years, the species loss has increased about 10 to 100 times, and that is what is known. I mean, seem to have started this 6 mass extinction, and a lot of studies now support. Initially, of course, there is again doubt about whether it is a part of the natural process happening or this is due to human interventions, and or whether it is really something different from the background. So now I think the speculation is off, and the measurement of these from various different studies indicate that these loss is much above the background that you would have expected. And so how did we actually land up in this gigantic mass? So this question was often asked: how critical is this 1 degree centigrade per year increase of global mean temperature during the past century, is it very different? Did we not see anything like that in the past 4.6 billion years? Probably not. That is partly because the data is not there, and because in the earlier days, before let us say 500 million years, the construction of climate data is very difficult, and we can actually have good amount of, some idea about the mean temperature, but the resolution with which you can get will be much coarser. As a result, the 100-year change we cannot measure, but from the change in the mean temperatures, it is we know that there is no indication of such change in the past. So, and it is also because it is today due to, we are in the what we call Anthropocene. This is a time when the environment has been degraded by the direct action of the human population on Earth, and that is why it is more serious. And I'll show you that this is directly related to the human influence on this action. So let me put this in the perspective a little bit. A unique place in the world, which is blue ocean, white clouds, and green land, and atmosphere. Atmosphere of greenhouse effect for life to sustain and thrive. And also its temperature is the mean temperature such that the water can have all these in the 3 different states, and that makes the heat transformation from one to the other phase, and that changes the heating over the land, produces winds, and these winds can then redistribute the heat. So everything is in such a way that it is a beautiful balance that actually helps sustain life on Earth. But humans' history is only about 12,000 years old. But from the Earth has evolved over 4.6 billion years, and within 12,000 years, after humans have become significant and grown, the environment has degraded so rapidly, there is no comparison in the past, and that is what is our problem. For example, Earth had several evolution history. A long time ago, there was not even oxygen, and oxygen started building up after the volcanic activity put water vapor and carbon dioxide in the atmosphere. The ocean formed, then cyanobacteria formed in the shallow ocean, and then started producing oxygen, and then the oxygen started building up. Only about 0.85 billion years, the oxygen started becoming. That is when the life started forming in the and of course it took a long time to do that. But over the last 500 million years, if you see half a billion history, Earth has been cooling very slowly, and it is cooling. And during this time, the temperature, this variation of temperature of the cooling was very much related to also how the carbon dioxide was in the atmosphere. So this temperature in the past were always related to carbon dioxide in some way or the other. Okay, but by different mechanisms. Okay, so until then, until about 3 million years ago, million years ago, the temperature sort of there's episodic variations of these events, but no oscillations like this in the recent times that we have. The ice ages, and by about 3 million years, we started having these oscillations. These oscillations are due to the solar variations as a result of the different astronomical parameters of the Earth. There's the eccentricity of the Earth's orbit, and this and the tilt and the gyration. Those affect this, how much solar radiation is received at different latitude, and they can influence the radiation balance. but their influence is such that if the mean temperature is higher than at a critical value, they cannot produce a negative feedback and take them to the ISSS kind of thing. And as a result, this did not happen when there is orbital parameters were changing over this period also, but nothing happened because the mean temperature is high. And when the mean temperature came to a level where, at present level, then these orbital parameters of the Earth could influence the solar heating, heat balance at the surface and produce these negative feedbacks. And that is how these oscillations and the stability of the atmosphere climate happened over the last 3 million years. The first about 3 to 2 million years, there is a 42-year cycle. Now in the last 1 million years, we had this 100-year cycle of ice, glacial and interglacial period. Then we started. These are, of course, just for you, for the readers' benefit. The scale of these are very different. Different sections have been, different scales have been used to highlight the variations. The recent, this is like just 20,000, and here the resolution was like 100,000 to 20,000 in this place and so on. But this pass is like just 20,000 years. And this is where we are recovering from the last glacial maximum, and we are now in interglacial phase, which is equivalent to about 3 million years that temperature that we had, right? So we are in this critical phase. This is why I wanted to put this figure to this, so that this mean temperature is very critical for the stability of the atmosphere, but stability of our climate. Now we see that we have already, and their projected thing is that temperature is going to go in by 2100 to about another 2 to 3 degrees above this, and then by 2000 another 100 years, maybe even 6 degrees. So that is the scary part. So this, once it goes to 200, then we are already here in this place. So now it will not be able to, if it goes to 2 degrees above this, we will be in this equilibrium state, and then none of these will be able to bring us back to a colder climate. So, and that is the main issue. And they have all affected, are related to the carbon dioxide in the atmosphere. The difference is being added by human activity. These are all by different natural processes that our this period. So none of these, that is also a very, very critical point. So over the last 10,000 years, the human population has increased, as Dr. Talukdar has mentioned that, but it has exploded in the last 200 years. And this is where, and until maybe 1,000 years ago, I think we are still doing something sustainable. The humans were using the environmental resources in a way that was somewhat sustainable. But today, the explosion of the human being is made us impossible to live with that, and the degradation has taken place slowly with the human beings, as Dr. Talukdar mentioned in the morning, that it started with our agricultural effect early on in 10,000 years ago. So we needed to clear the land from the clear forest to create land for agriculture. So that started increasing, putting already carbon dioxide into the atmosphere. Then to sustain agricultural activity, so we cleared land. To sustain more growth of population, we had to produce more domesticated animals. Domesticated animals also require grazing, so you clear more forests. So domesticated animals increased and wild animals decreased. So all these things are adding methane and carbon dioxide into the atmosphere. Of course, it has as a result, biodiversity loss and increase of carbon dioxide is taking place. But the explosion took place in the last 200 years because in last 200 years, what happened is that we're not just simply exploiting the atmosphere or the surface of the atmosphere of the earth, surface resources, but we started exploiting all the natural resources under the surface. And we started finding more and more different ways to do it, because what happened is that there the more and to sustain more population, they need food. Food needs to be grown. That is one aspect. But to sustain them, they have to earn money. To earn money, they have to make jobs. In the name of creating jobs, we have started making industrialization, created all kinds of opportunities to create jobs, and to sustain the industries, you exploit the natural resources. You bring out all the resources from the earth, and then use create electricity, and the electricity runs the industries, and therefore, as a result, you are exploiting all the natural resources, and you have come to a stage where it is simply not sustainable, and that is where as a result of this. And the science has added to this, because science has given newer ways to exploit this. We have come up with newer ways to exploit it. Science is good; it has helped us, but it has also helped the degradation of the environment. And so the global population and the carbon dioxide is the slope of the global population and increase in the carbon dioxide is very similar, and that is very much related. And this is not sustainable, because the earth has a capacity, carrying capacity. The carrying capacity of the earth is something like sustaining about 200 million tons of vertebrate population. And about 1,000 years ago, 10,000 years ago, that is exactly what it was. About 2,000 humans and wild animals together, and all the vertebrates had about 2,000 million. 200 million tons, but slowly they started increasing, and today we have a vertebrate population which is about 5 times that, and it simply cannot sustain. And when you're overexploiting the sustainability in the sustainable resources, that the sustainability goes down, the carrying capacity goes down. Carrying capacity is affected, and you are overexploiting it. At some point of time, the system will simply collapse. And then when it collapses, you will not be able to neither sustain it nor be able to recover it back. And that is exactly what is beginning to happen today. With all the mass extinction and everything. Even I will imagine that COVID is part of this. Because of all the degradation of the environment and our exploitation of this, we have somehow created these newer diseases, and these diseases will contribute to this mass extinction, and that is the most important part. So it is not surprising that the mass extinction has set in, because human population. And the mass extinction is very much closely related to the large increase of human population in the last 200 years. Why you should be worried? Because this is actually a different mass extinction, because this is the only mass extinction where humans are contributing very seriously, and the only humans are contributing, and humans are very, very selfish, and they're very intelligent animals, right? But they are selfish and greedy, and that is why it is difficult to create policies to overcome this, and that is our main challenge, and that is what is going to be our destiny. I think that is the. So there is evidence that now the COVID is also actually accelerating this mass extinction. I don't want to. So let me just conclude by saying what is my take. My take on all this is you have to first deal with two different aspects. Firstly, the larger, broader aspect, and the broader aspect of global warming. We must, if humans have to survive, the climate change must be stopped and reversed, and soon, before it is too late. And so what needs to be done? We must bring the greenhouse gas emission to zero by 2050. If we cannot do that, then we cannot stop the increase of global mean temperature to more than 2 degrees by the end of the century, and then there will be no turning back. And we have to do a lot of other things, and just that is not enough. So we have to convert ourselves to 100% energy from renewable sources, make all instruments, engines, factories energy efficient, so that we can do things with less, with smaller energies. So that is where the research should be, and not in this, not in the in coming up with new smartphones and coming up with all kinds of all these social media things. This, I think, also is a big distraction, and that is another thing that is actually also using up a lot of energy, because to store all these the clouds of computers all over the world and then keep running them is a huge amount of energy that is being used, and that is also adding to the climate change. And therefore, I think we have to get away from all this. We must make some very tough decisions and very tough changes in the lifestyle. Finally, I think without lifestyle, the government cannot do everything, as Dr. Tarada mentioned in the beginning. We have to contribute. Everybody has to contribute. But that is, government must make some tough policies so that these lifestyles, we have to change our lifestyle. Unless we go back to the basics, there is no way. If we keep on using the same current lifestyle, then the energy requirement will not come down. If the energy requirement does not come down, there is no possibility of bringing down greenhouse gas emissions. Then there is no way of stopping the climate change. And and this is where I think we can all contribute. We of course will contribute, and we are contributing. The poorer section of the society is actually contributing. I don't blame that, because they are not using that much energy. The maximum energy is being used by the rich, and the rich people have to contribute much more, but they are not going to do that unless we mandate them to do. And that is where the government policies must come in. But government policies are also unlikely to come in, because they depend on the rich people for all kinds of things. So this is where we have to change. We have to convince the government. If for survival, we need to make these lifestyle changes. And the lifestyle changes need certain policies to implement, and that government has to help, and we have to all contribute. And the rich also must recognize that for the next generation, unless they do this, they will not be sustainable. So, and for Brahmaputra and others, I have my own strategy, but I'll just mention one thing. That other thing that this policy makers, and there are of course a lot of climate skeptics, but they will always raise questions, and the policymakers might sometimes take their view as an escape route. But I think decision makers today must realize that we have to make decisions based on probability. And most of the time, the excuse given us that you cannot give us an exact number of what will happen to this or that using your models. And I say that this we cannot give, but we can give the probability. This I cannot give because the climate system, this is the nature of the system. The climate system is so complex that nobody will ever be able to give a deterministic number that, okay, global temperature will change only exactly by 2 degrees. But it will have a range. That range should be, and we have to have a confidence in that range. And with that confidence in the range, we should be able to make decisions, because you always make decisions like that based on probability. In all other fields like stock market, even you make based on policy, based on probability. But when it comes to climate change, we do not make policies based on probability. And this is ridiculous in my opinion. And policymakers must listen to this and make policy based on these probabilities. And that is one thing. But if the policymakers don't do that, then it is our duty to convince. And that is where we need to be active locally and do our best. At the same time, try to convince the policymakers to take necessary decisions. In terms of the Northeast region climate, the flood in this Northeast region, I have a suggestion that we can go from we can actually, so far what has been sorry, I think because I could not do this in full screen. So can you see it? Can everybody see this?
Yes, sir.
Okay.
You can see this.
Okay. So what I'm proposing is that for the Northeast flood, the general policy has been that we'll control the flood. But the flood in Assam, because of the size of Brahmaputra, the size of the tributaries, and the amount of rainfall that takes place in this region, is not going to be possible any time in the future. And I think it is almost not a possible solution. So what we need to do is we have to go from flood control regime to flood management regime. So this is the kind of adaptation strategy. So the risk management has to do with the adaptation. So the adaptation to the flood has to minimize the risk. What we can do is, instead of building embankments, we build shelters and give proper, skillful flood forecast, which is possible. And if we give flood forecast and if we build shelters in various places in the villages where there are flood-prone villages, and these shelters can be associated with oh, sorry. Is this gone?
We can still see this, sir.
I can see this. Okay. Okay. So the floods, this can be built over the in villages where there are schools, maybe because we have this experience with cyclone shelters, tropical cyclone shelters in Andhra Pradesh and Orissa, and they have become really, now the cyclone forecasts have become good. As a result of that, the evacuation has become more efficient, and then evacuation then put the people into the shelters. As a result, the loss of life has completely reduced today. Same thing can be done for floods in Assam by building more and more. We should simply go from embankment building to shelter making, and then every year if we make 5-10 shelters all over different villages, I think they will completely make people adapt to these variations because they are only for normally about few days, and that can be actually very, very useful, and they can overcome that period. So we can help them build the sort of flood resistant houses, and then when this when the flood comes, actually evacuate them to shelters and make sure that the houses are not very much damaged. So that also is possible to do. So I think that is a strategy that the government should adopt, in my opinion. And our flood risk management people can suggest that. So with that, I think I'll stop. I think I have taken much more than I should have. And thank you very much. And maybe if there is any question by anybody, I would be happy to.
Thank you so much, sir, for such a delightful and elaborative presentation, and such a relevant topic you have covered. We actually have been bombarded with a lot of questions, so I'm not sure how far we can just allow all the questions for our resource person. Let me start with, yes, some of the questions I have got at the first place.
Okay.
So the first question is coming from Ruma Talukdar, Cotton University, Assam. So she's asking, while the research on climate change and its impact have been carried out very seriously globally.
Can I just interrupt?
Yes.
Actually, she wrote again that this answer already sir had given during the process.
Okay.
So she has put up a different question actually.
Oh, okay. So if you have the question, please.
Yeah.
Thank you, Sunandam.
Yeah, Ruma, can you ask the question yourself then?
Yeah.
Okay. Actually, it's something like some specific question.
Yes.
Like, what are the challenges in conducting such research on climate change, of course, in Assam? Secondly, does the climate scenario of Assam may affect significantly the national results?
Okay. So there are a lot of challenges in climate research in Northeast region, partly because of non-availability of data. Good data is a little bit difficult. Although India boasts about good rainfall data over the more than 150 years over different parts of the country. And that is because the British had actually set up a very good set of rain gauge network. And then after independence, the government has reinforced them and added more. As a result, now we have a very good network of rain gauge stations all over the country. And in the recent years, now many of the states also have added more and more, making that network very good. However, and that goes back to almost about 150 years. Okay, so about 150 years of good data, daily data is available. Rainfall, that is one of the critical parameter for studying climate change. Okay, temperature data is reasonably okay, because temperature it does not change very much from one place to another place. The temperature changes rather slowly, but rainfall can change spatially very rapidly. As a result, we need more observation for rainfall to get even the mean correctly. So, and to get the extremes, you need daily data. So, you need daily rainfall data at high resolution over the whole country. This is reasonably covered in the rest of the country, but in Northeast it is not. It is the main problem in Northeast is because of our topography and inaccessibility, and because we have a sort of what I call mesoscale orography. These are many mountains which are about 1 to 2 kilometers high, and in between there is only 200, 300 kilometer space. Another mountain comes in. So there are many such mountains, and these mountains actually can affect the local rainfall significantly. And the mountains can produce, and as a result, we need a much finer network of rain gauge stations, but it is not there. And therefore, it's a big challenge to actually construct the rainfall record over this in this region. Because in Arunachal Pradesh and places like that, in Nagaland, Manipur also, only in the valley there are a few stations which have long records. Even in those stations, if you go back to 30, 40 years back, there is not much record because they are all disrupted. Only there are big gaps and no record. So we could find only about 10 stations, 10 or 15 stations for a period of about 30, 40 years. But there is not more than that. But we need about 100 years of record, 100 years of record so there is no this is a big challenge. fortunately, I think Professor Ravi Mohanto has done some good work in data mining and creating a longer daily rainfall network data set over here. So instead of only 10 or 15 stations, now we have 24 stations over which is distributed over this country, and for about 90 years, daily rainfall data. And this is actually a very valuable set of data. Now, how did he get it? How did he do it? So this was very interesting, because what we have is, so these are all stations actually IMD maintained stations, but there is no data beyond a point of time, and there is also a lot of gaps. So we had to fill up gaps, and then we had to extend the data to 90 years, from 30 years to 90 years. So this has been done by looking at, because Assam has an important resource. We have a lot of tea gardens. These tea gardens have their own measurements. Every tea garden has a rain gauge.
Yes.
They will maintain the rainfall record, and they keep it. They will write by hand and write in ledgers. So there are some old ledgers stored in their archive somewhere. So we can dig up those ledgers and actually find the rain gauge record. And he has done that with some students for all these. And this has been a very enormous, huge job. And at the end of the day, so we have identified within 20 kilometers of that station, if there is a tea garden, we collect the data from there. And if there is more than one tea garden, we collect data from all the tea gardens, do an average, and then create a record of rainfall on that particular day. And like that, you fill up all the dates like that. And so it has been possible to do in some of those stations, but there is not always. Other places it is still not possible. So we are not been able to do more than 24. And there's still gap areas, like in some parts of Arunachal Pradesh and some parts of western Assam, northwestern Assam. So, and of course, Nagaland, we have to get more data from there. So there are issues like that. That is one major issue. But other issue is, of course, studying climate change impact on various different things. Like we need data for to understand the impact in the past, how the the record of how much discharge, Brahmaputra discharge took place over the last 100 years. That data is also not available because Water Commission doesn't give that data. There is no reliable data or water discharge over the past. And then there is no data on biodiversity. There is no, how do you study biodiversity, impact on biodiversity? There is no data record on biodiversity on a longer time scale. People have done some bits and pieces here and there, but there is no data, baseline data, and there is a lot of different aspects of biodiversity that need to be covered, but there is really almost nil data. So these are basic data is the main challenge, but also challenge is the human resource, because there is nobody who studies this. I don't see anybody who is trying to study this in a scientific manner, and so there is no climate science research in this place. So that is one thing. As a result, there is no interaction between climate science people and the biologists. So this is all is a sort of is a challenge. So you need people who is seriously interested in doing these things. So one major challenge is, of course, there are not enough people on climate experts who is interested in doing and working in this region. The problem is that the Northeast climate is very, very, very interesting, important. But look at the as in comparison with the Indian climate monsoon itself. This is a small part, very small part. Although it is a high rainfall area, the region is small. So therefore, even monsoon people do not pay enough attention to in the Northeast. Okay, The global people will not produce any, put any interest on this, right? But so we have to do it. People over this region has to do it, and then there is no experts. So this is our problem. Challenge is this. So we have to build expertise, and then address these questions. So there are many challenges. As far as how this can impact the sort of monsoon in general, there is definitely a linkage of northeast with monsoon. Northeast is a part of Indian monsoon, but it tends to go out of phase with the rest of India. So it is a part of Indian monsoon, but whenever there is the rest of India is monsoon is strong, the northeast monsoon tends to be weak, and vice versa on an interannual time scale. And even on a decadal, multi-decadal time scale, we have seen that whenever the rest of India is strong, or the monsoon is very strong, then the northeast will be weak during that period. So this is a very interesting aspect of northeast monsoon. So northeast India climate is scientifically also interesting. There is a lot to be learned. The clouds in this region are very, very different because of the orography, and how they produce rainfall is not very well known. So the cloud and precipitation processes in this region needs to be understood. Not much is done. So there is a lot of interesting science problems that we need to address in this region, and still not very well understood. Therefore, scientifically, this is a very interesting place, and there is a lot to be done.
Thank you, sir.
Thank you, sir.
Can we have one more question? Sir, it is one question related to the glacial, interglacial cone data that you had shown.
Yes.
In of the slides. So in the slides, if I'm not mistaken, I saw some eight events in history.
Right.
So in each of these events, we could see a rise in the concentration level of carbon dioxide and then a sudden drop. Is it, sir?
So the rise is, so these are bought from. Okay, go ahead and ask your question.
So as per the current rise, I could see the rise is almost twice the rise that had taken place earlier, but still we have not seen the drop.
No. Partly that is not twice. It's just above the mean level of the past. The twice is because the extrapolation in the future. Because the scale is so small. Okay. Extrapolation in the next 50 years, 100 years. So extrapolation based on models.
Okay.
Based on models. What is the model telling us?
So in that case, sir, are we going to see a drop again?
No, that is what I'm telling you. That is what is the worry. The worry is that if we allow this to happen in the present rate of change, it will continue, and the carbon and the greenhouse gases are not reduced and reverted back from the atmosphere, then it is very unlikely that it will stop. And also the carbon dioxide, as I mentioned, in the atmosphere, it will still live for 100 years, even whatever is there. And that will keep on increasing the temperature, at least. So by the end of the century, we are not going to be seeing less than 2 degrees increase of temperature. And if we do not see less than 2 degrees increase of temperature by the end of the century, then we are in big trouble. Then we cannot bring it back.
Okay.
That is from the past experience. We can see, as I showed you in that curve, that if I reach the 2, then you are in a different regime altogether. And in that regime, the orbital parameters, orbital variations of the Earth will not be able to influence that mean to a level to cool down enough. Okay. So that is the main issue.
Okay, thank you, sir. Sir, if I may just, this is related to some of the reports that we could see that is published by IPCC periodically, that is coming out. So one of the questions is related to that often these reports are very difficult for common people to understand. So in the context of Northeast India or in our region, how important is these reports are published in regional languages, and how can we just make this awareness built up on these published documents, sir? Is there some sort of a
well, I think that is a very good point and very important point. Communication. The communication to general public. You have to bring it down, make the jargons, leave the jargons, but make the important points. Why? So, why? What is causing them and causing this rise, and why we should convince the people, the grassroots people also, the farmers and other people who are. But as I said, this is important. But as I said, it is not so important to convince the people. They are already convinced. They are not worried. The lower rank of the people, the poor, the farmers, they are not so difficult to convince. They get convinced. But the communication is still very, very important, and there are many people now doing that job already. So translate this into a simple language and so that it can be communicated. So we should have also interaction with the farmers and the growers and so on. But I think most important thing is to convince the rich and industrialists. They have to change.
Yes.
Without them, it is not going to change, because they are the most consumers of the energy. Energy consumption has to go down. We have to reduce energy consumption. If we have to reduce, if we keep maintain the energy consumption at that level, and the renewable energy is not coming at the same rate as the energy demand is increasing. Okay, we need energy demand is increasing for so-called developmental activities. So the energy demand must go down. Whether it is developmental or not, we have to reduce energy demand. And that is why the lifestyle change is required. Lifestyle doesn't only mean just the lifestyle. Lifestyle means everything has to change, in my opinion. The way we do few things. We are always in the fast track today, right? We can't wait for things. We have to travel by airplane. We cannot wait to travel by train or right, because the life has become fast. All these things have to change. Otherwise, energy demand will not go down. So, and the people like the politicians have to do campaigning using their helicopters. The private people have to run their jets to go from one place to the other place of the world. These things all have to change. Otherwise, energy demand is not going to come down. So this is where we need convincing the rich, not the poor. The poor is already convinced. There is no issue about that. It is basically crux of the problem is the energy demand. Unless energy demand goes down, greenhouse gas in the atmosphere is not going to come down. And that, in the long term, this energy demand has to go down. And that requires a drastic change in the lifestyle or our social style. I think that is why I mentioned that even our dependence on this digital world, like social media and all these, so it is actually, the lifestyle has changed. Remember, today we are depending on ordering through the through your app, sitting at home, go to Amazon, get everything. You don't have to even walk to your neighboring stores, right? You don't go because you can get it done. Do you know that also is adding energy demand? Amazon cannot give you these without spending energy.
Yes.
They have transportation cost and all that, so transportation is required. They have to fly the goods to the aircraft, and then so that is causing energy. This is something that we need to change. This whole lifestyle has to change. Even our middle class is using a lot of energy, which we have to change, and that is, I think, is a bigger problem. So I think we are stuck with a very serious situation, and unless we do something very, very drastic, we are stuck in a very grim situation. And we'll pass away. You know, we the older people will go away in the next 20 years. We'll be out of this world. But what will happen to the children? What will be their life? So we have to see that, and that is where the main problem is.
Okay. So I think we can take one more question. If Rituraj, do you have a question for sir, or in someone else? Okay. So so if I may, just one last question, sir.
Okay.
So we are often hearing about the carbon building up carbon sinkages where we can store the carbon dioxide, greenhouse gases. So is there a thought right now, maybe just a wild guess, maybe we can just puncture out these responsible gases out of the atmosphere somehow or the other way?
Yeah. Well, there are two possibilities. People are, thinking and trying, but to my knowledge, both of them are not a sustainable development. It is simply to satisfy our sort of temporary ego. One possibility is like carbon dioxide sequestration. So you pull the carbon dioxide out of atmosphere by some means and put it into some place where it will stay in the ocean or under the ground, somewhere where it will stay for longer time. So this has not proved very, very efficient, because most of the time they will come back to atmosphere again in a short period of time. So this is the main problem. There is also storing carbon dioxide someplace. You have to make them absorb somewhere. So absorbing carbon dioxide everything has a saturation limit, right? So you have to find something which will absorb carbon dioxide more, so that they and hold it back in that place. And that is a very challenging problem. We have not found very good sources. Secondly, whatever we have found, those have the tendency to release back to atmosphere at such a short period, not in century scale, but in decadal scale. So that kind of a thing is still a problematic. It is not a solution. And the other solution people are thinking about is to sort of cool the earth by artificial means, like putting aerosols in put some big reflector at the top of the atmosphere, so that solar energy does not reach the earth as much as it does, and so that a larger fraction gets affected, so the earth will cool down, and then still you can go on misusing the carbon dioxide and then lead your life. So this is preferred by the oil lobby and everybody else. I think they would prefer that, because they will continue to burn the oil and create it, but still they will manage that. Okay, temperature has not increased, but that is not a solution in my opinion. So this is called geoengineering. So there is a lot of geoengineering solution. None of this geoengineering solution is very satisfying, because partly they are not very clear that they will not affect the climate in a other way and actually make it worse. Okay, because you can put aerosols in the stratosphere, but the aerosols in the stratosphere will cool down, no doubt. Some sulfate aerosols in the stratosphere will cool down, but sulfate aerosols will also react with some of the gases there, can produce other serious problems. Maybe they will deplete the ozone so much that life will become very difficult. So those things are not proven directly. What is the other potential negative effect of these? So that is not done, and they are not very ethical. These are not ethical solutions. So our solutions have to be ethical, and it is not something that simply because somebody wants, to make their pocket rich, we go and modify the atmosphere to suit them. So that is not correct. So So in both geoengineering solutions or carbon sequestration experiments have not yielded satisfying results so far. So, so I don't see any very strong candidate or alternative candidate than reducing the greenhouse gases and energy reduction. So I don't see that. But multiple interested parties are there. They will keep on arguing, and they will do. So we have to have a strong counter argument to those.
Yes. Yes, sir. Thank you very much. But if I may, just one more last question, sir. It may be a retrospective question. So after listening to your very nice lecture and presentation, and with some thoughts that we already are pondering upon, it seems that industrial revolution is largely to blame for global warming that we are facing right now. Is there some sort of conclusive conclusions that the world community has arrived upon the situation of civilization in the event that the industrial revolution at the first phase were not taking place at all? So would that have been a better place, or it would have been a worse place to live on right now?
Yeah, that's also a good question, but I don't have a good answer to that because it is a theoretical question, and then you have to. I can only venture my thought is that as you see, as I had shown you, these. Let me. I think. I'm not able to move this. I don't know. So in one of the cards, I have shown that the growth of the population about even 1,000 years ago was rather limited. As a result, it was still sustainable in some sense. Think about before 200 years. The main thing the science revolution has taken place in the last 200 years only. Before that, very little new, sort of. Science had come out, which had really made revolutionary changes, right? So those things were still sustainable in the sense that what the earth produces and how we can utilize those resources and still live. That much population is possible, probably sustainable. But it is the population growth which demanded to come up with new. As the population grew, simultaneously the science also produced new ideas to survive and exploit the environment and create tools to survive, and jobs, industries and everything. So these two things went together. The large increase of population as well as the new inventions, science inventions. The science inventions have given us new ideas. The electricity came in, and so motorization took place. Then all that really revolutionized, right? So a lot of new things that industries have started building up. So this is something unknowingly at that point. I think we never thought that okay, this will really become such a bad thing, because even 200 years ago when it started, that time still the growth the global mean temperature increase was still very, very small. Just 0.1, 0.2 degrees or something, very, very small. We could not really make a big difference. But within the last 100 years, in fact, last 50 years, it has become explosive. So last 50 years has been the sort of rate of growth of global mean temperature has been extraordinary. Earlier that it is a non-linear growth, very slow growth, and suddenly it become high in the last 50 years. So it's a very hard question to answer, but I would say that if we remained at that level and not and population, if population and we did not invent, then what will happen? The growth of population, there will be more death, and therefore the population will not grow as much. Okay, so if there is no, because see, as with the science invention, where our life-saving drugs also started coming, right? So the life expectancy grew. Suppose we did not invent all those, what would have happened? People will die younger, more people will die. even if we are producing, then there will be some sort of a sustainability, natural sustainability. Food will be less, therefore people will also die because of that. And then therefore, even if you try to grow, there will be death rate will be larger than the growth rate, and therefore somehow there will be balance. So there will be a very complicated social balance will take place. So probably it will remain sustainable, but that is what it might happen. But probably the environmental degradation will not take place. The global warming would not have happened.
Yes.
So it's a hypothetical still, but that is the hazard. I can hazard that kind of a guess.
Yes. So thank you so much.
May I have a question, please, sir, if you kindly allow me?
Okay.
Thank you, sir. This is Rituraj Dutt from AdtU. So my question is more with the disaster part. So as you have discussed that for the last 50 years, we have observed that local extreme events have really increased in their frequency. And as a developing nation, our economy is not yet that good so that we can build engineering infrastructure or we can have a resilient society. So, sir, in this juncture, what should be the responsibility of the academic institutions like ours, where we can help the society build resilience or reduce the impact?
Right. So, resilience means adaptability. Okay. So, if we do, basically, as I said, unless the global community act in a very big way, the climate change will not stop. Okay. So as a result, we are going to face very serious consequences in the next. The extreme events are going to increase, the floods are going to be more, and so on and so forth. Now we have to be able to, we have to find ways and means how to minimize the damage and live with it. That is the adaptability. So we have to advise them. We have to also devise new ways to help adapt to this. So like we have to help the poor people to build flood resistant houses. Okay, even if it is cost a little more, but somehow they build, and then use as I said, the lifestyle has to, our lifestyle is always not very, the poorer section of the population does not have a very extravagant lifestyle, but still we might have to adjust to the lifestyle. But we have to adapt to these changes, temperature changes, and so for that, certain amount of research is also required. What will be the best strategy? As I said, I have given an idea of the adaptation to the floods, and these the building shelters and educating people about the flood forecast. So today, even flood forecasts are given by even Google. Google is trying to give flood forecasting, okay, because they have the technology. But the problem is that this is now being distributed through the Red Cross. But this is not scientifically validated forecasts. They have, because they have a lot of data, right? They have the data of the topography, the places, and everything, and so they have developed some models. But they need to be validated for the region, and therefore to have confidence in their flood forecast, some validation exercise, and I have not seen those validation, but now being distributed in a global, all over the country through Red Cross, and government has allowed it. And I have actually questioned that. This is the kind of thing that scientifically you have to question and come up with actually useful and validated forecasts that is useful for the community. Then only they will build confidence on those forecasts, because all this adaptation will require forecasting, confidence of forecasts. So these we have to communicate with those people who will be the beneficiaries, and make sure that these forecasts are skillful, they are validated, and then communicate them to adapt to these kind of situations. So this is like these are things that we should do. There's a lot to be done in this area, I think, and there is a lot of research is actually required to come up with different ways of doing it. I have only given one idea, that may not be the only idea. There may be other ideas which, and there is research required on that. So this is also a disaster risk management strategy. Disaster risk management strategy. Disaster management authorities should do a lot of research or sponsor research to come up with new ideas to do that, and education institutions can do that, because you can estimate disaster risk in different ways. And this is one study. I have not seen much of that in this region. So the academic institutions can at least do disaster risk management strategy studies, disaster risk assessment studies, and these are quantifiable, so that they are quantifiable. What kind of, how much risk is there to a particular impact, a particular event, and that requires also very serious scientific study. It is not, and I have not seen one single report of that in this direction. So there is some old report done by international communities on a gross way, but it needs to be done on a micro scale on various different regions, and so that's one region area that I think academic community can definitely help. For that, it will require certain collecting appropriate data, which may not be available. You have to make effort to get that, and do the kind of, so even doing that properly will be actually useful scientific study, which can be published in peer-reviewed journal. So these need to be done very scientifically.
Thank you, sir. Thank you very much.
So we have almost come to the closing part of this inaugural session. I'd like to invite one of the organizations, Navanita. Would you go on with the vote of thanks, please?
Good afternoon, everyone. I am Navanita Demari, Assistant Professor, Civil Engineering Program. I'm here on behalf of Faculty of Engineering and Technology to give a vote of thanks for today's session. I would like to thank our resource person, Professor P.N. Goswami sir, for enlightening us with his knowledge. Sir, your lecture was full of knowledge and it was very informative. It gave deep insights into the topic. I'm pretty sure that the precious knowledge that Professor B.N. Goswami sir gave us will definitely help us in future. Once again, I would like to thank Professor B.N. Goswami sir for taking out time from his busy schedule and enlightening us. Thank you so much, sir. I would also like to thank our Chief Patron, Dr. Anandatta sir, Chancellor AdtU, Patron Professor N.C. Talukdar sir, Vice Chancellor AdtU. I'm thankful to the organizing team, faculties, and all the participants present in the session. Thank you once again to all. With this, we have come to the end of our first session. We shall meet in the next session, which will start from 2 p.m. Thank you all.
Thank you, sir.
Thank you. Thank you.
Thank you so much.
Thank you. Thank you, Arnab. Thank you.
Thank you so much, sir.
Bye.
Bye-bye. Okay, so the link will be the same. Let us meet at 2 o'clock.
Am I audible?
Yes, Rituraj, I can hear you.
Okay, sir. Thank you. I think Dr. Mitesh has joined us.
Yes, yes, I have joined already.
Yeah,
Okay.
good afternoon, Dr. Mitesh.
Good afternoon, everyone.
Thank you, Dr. Mitesh, for joining us today. Let us wait for 2 minutes and let's see if we have some more participants, then we'll start the proceeding.
Sure, sure.
Chairman, sir, we have 20 faculty, we have 20 participants. Can we join? Can I start? Okay, sir. Thank you. Thank you. So again, I welcome everyone. On behalf of the organizing team, I welcome everyone to the second session of our FDP on climate change challenges and disaster risk reduction. So in this particular session, we have with us Dr. Mitesh Surana from IIT Roper. The title of the talk for Dr. Mitesh Surana is Promoting Traditional Building Construction, a Sustainable Way of Earthquake Risk Reduction. So Allow me to kindly introduce Dr. Mitesh Surana with everyone. Dr. Mitesh Surana is currently working as an assistant professor in the structural group in the Department of Civil Engineering, Indian Institute of Technology, Ropar, since 2019. Dr. Surana did his BTech in Civil Engineering from Engineering College, Kota in 2011, followed by Masters and PhD in Structural Dynamics from Earthquake Engineering Department, IIT Roorkee. Dr. Surana's research work includes seismic characterization and vulnerability assessment of housing stock in hilly regions of India. Dr. Surana's other research interests include performance-based seismic design of non-structural components, and earthquake loss estimation. Dr. Surana has published more than 25 peer-reviewed articles in national and international journals, and he is also the recipient of Indian Services of Engineers Award by IIT Roorkee. On behalf of everyone, I would like to thank Dr. Mitesh Surana for kindly sharing his valuable time with us, and I hope this discussion or his lecture will be of very helpful to all of us. So over to you, Dr. Surana, and thank you very much.
Okay, thank you, Dr. Nath, for introducing me. So let me share my screen. So are you able to see my screen?
It's yeah, we can see it now.
Okay, so am I audible?
Yeah,
my voice is clear? Okay.
Yeah,
okay.
it is clear. Thank you.
Okay, so good afternoon, everyone. As Dr. Nath has already introduced, that I will be discussing about promoting traditional building construction, which is a sustainable way of earthquake risk reduction. So although my expertise is related to earthquake risk reduction, but I will try to connect it with the theme program, that is also climate change challenges. So I will try to relate this presentation with climate change challenges as well. So before starting the presentation, let me introduce with the keywords which are associated with this presentation. So if you see here, so there are two keywords I can take about this. First one is the traditional building, and the second keyword is earthquake risk reduction. So these are the two keywords which I am going to focus in this lecture. So now let us first discuss about what earthquake risk is. So it is the predicting likely consequences of an earthquake to a society, to a nation, to a city. So it can be estimated at any scale. So we are trying to predict what will be the likely consequences of an earthquake to a given city, region, or a society. So naturally, there are different ways to estimate earthquake risk. So there are two major methods by which this earthquake risk can be estimated. The first method is mainly what we call deterministic method, and the second method what we call is the probabilistic method. So when we determine the earthquake risk using some deterministic method, then that type of assessment we call earthquake loss estimation. Whereas when we determine it using probabilistic method, then a specific terminology, seismic risk assessment, is used. So these are the two different terminologies which we often use to estimate earthquake risk. One is called earthquake loss estimation, which is a deterministic measure, and another one is seismic risk assessment, which is a probabilistic measure. So let us now try to understand that what are the different components of earthquake, on what factors this earthquake risk depends on. So there are three major factors which mainly contributes to this earthquake risk. So first is the seismic hazard. So hazard we usually represent by the expected level of ground shaking that can occur at a particular site. So if you are familiar with Indian seismic zoning map, here this representing the Indian seismic zoning map, where we can see that whole of our Himalayan belt and part northeast as well as the northern states of Jammu Kashmir, Himachal Pradesh and Uttarakhand. So mostly they are either in zone 4 or seismic zone 5. So zone 4 corresponds to, according to Indian seismic zoning map, corresponds to a peak ground acceleration of 24% of the acceleration due to gravity, whereas the zone 5 corresponds to a peak ground acceleration of 36% as that corresponding to the acceleration due to gravity. Similarly, so from this we can conclude that the Indian Himalayan region is subjected to high seismic hazard. Now let us try to understand what seismic vulnerability is. So seismic vulnerability represents the damageability of a structure. So what will be the damage in a structure when it is subjected to a certain level of ground shaking? So this seismic vulnerability of a structure we try to quantify using seismic fragility curve, and when we wanted to convert from damage to loss, then we use the loss curve. So these are the two pictures which are showing the typical plots of fragility curves of a structure and also the loss curves or vulnerability curves of a structure. So fragility curves directly gives us the damage, whereas the vulnerability curves gives us the loss, how much loss is going to occur. Then the third contributor to this seismic risk is exposure. That means how many buildings, how many population, what floor area of the building will be exposed to earthquake effects. So that includes that data are included in the exposure model. So we can see that the seismic risk is a joint function of seismic hazard, seismic vulnerability, and exposure. So naturally the question is how we can reduce the seismic risk. So because seismic hazard cannot be reduced, it is a natural phenomena, we cannot control the seismic hazard. To some extent exposure can be controlled but not fully. So only possible way to reduce seismic hazard is to reduce seismic vulnerability of the structure. That's why for any earthquake risk reduction program, seismic vulnerability reduction of infrastructure becomes very, very essential. So first important lesson is that to reduce seismic risk, somehow we need to focus on reducing seismic vulnerability of the infrastructure. That is the main idea of reducing the seismic risk. Now trying to connect it with what traditional buildings are and then how we can implement the earthquake risk reduction, achieve earthquake risk reduction through traditional buildings. So let us try to understand the traditional construction. So as we already know that India has very rich heritage in traditional or vernacular building construction. So traditional construction means we are discussing about the construction types which are in which the buildings are constructed using the naturally occurring locally available materials such as stones, wood, timber, mud, etc. So here I have included some typical photographs of traditional buildings which are prevalent in Himachal Pradesh. Similar kind of buildings you can also find in Assam, for example, Assam type of housing. Then in other northeast part we can have Naga type of housing, and there are some other local regional names to other housing types as well. So all these traditional construction practices utilizes the materials which are locally available. This is one of the greatest advantage of these traditional construction practices. The second thing is, if we can see here that the first building is a dressed stone building in which the wooden members are used to reduce the span of the walls. So therefore, this is one of the efficient way to make or increase the effectiveness of the walls against the earthquake loads by reducing the vertical span of the wall. So here the bands are provided which provides the box section of the building as a whole. So this building behaves just like a box. Second figure you can see the Thatra building. So in this Thatra building you can see the use of wooden elements extensively, and for roofing purpose they are either using stone slates or GI sheets. So then third type of building you can see here the dry stone construction in which only stones are used which are rubble in nature. So in first case Kathkunni construction the stones are dressed stones, whereas in the dry stone construction these are the random rubble stones. Then the fourth case you can see the mud wall buildings in which rammed earth is used to construct the buildings. So a number of these type of buildings are evolved in India over the past centuries, out of which during field visits we have observed that some of the buildings are as old as 300 years. They are existing from past 300 years, and they have proven earthquake resistance because they have survived many earthquakes which has already occurred in these regions. So the current trend in the region is changing because now people are moving towards the contemporary counterparts of building construction. For example, they are moving towards reinforced concrete or masonry building construction. But what are the problems associated with those construction? That we will discuss from the point of view of the climate. So if we see that the construction sector only shares only 40% of the global greenhouse gas emission. So this is one of the remarkable number, that 40% of the greenhouse gas emissions is coming from the construction sector only. And if we see the plot on the right hand side, we can see that how the cement production globally has increased in past 5 decades. So if you look at in 1970s, the cement production was around 500 million metric tons, which has reached to around more than 4,000 million metric tons in 2020. So this is a global estimate of the cement production, which has increased over the year. Sorry. So as we already know that the cement is one of the responsible constituent material for CO2 emission. So therefore the carbon dioxide emission from the cement has risen significantly over the past few decades. So some studies suggest that the promoting traditional building construction practices can reduce the emission of these greenhouse gases to a significant extent. That can be reduced by up to 2/3, a magnitude of 2/3. So traditional, over and above that, traditional constructions are weather resistant, cost effective. They also address the socio-economic aspects of the communities, as well as they prevent the culture and also have low carbon footprint. Therefore, it becomes very essential to understand that how we can make use of traditional building practices to fulfill the housing needs of the occupants. So now let us try to understand that what are the different types of traditional construction those exist in the Indian Himalayan region. So I have specifically considered the Himachal Pradesh, where we have identified few traditional building types. So I will be sharing the details of those traditional building types, that what type of buildings exist in those regions. So first type of the building is what we call dry stone buildings. So what these dry stone buildings are? Let us try to see. Sorry. So first of all, I would like to mention that these are the buildings which are prevalently found in 3 districts of Himachal Pradesh. Those districts are Chamba, Kangra, and Shimla. So all these districts are lying in either seismic zone 4 or seismic zone 5 according to seismic zoning map of India. So that means these regions are characterized by high seismicity. So you can see here these blue color dots are showing the regions where these dry stone buildings are prevalent in Chamba, Kangra, and Shimla district. So now let us try to understand what are their different architectural and structural characteristics which makes them earthquake resilient, and what are the features which makes them vulnerable to earthquakes. So we will try to understand both of them simultaneously. So the basic principle of earthquake safety is that the constructed building should be as regular as possible. Therefore, that means its plan and elevation should belong to a regular type of geometry. That means square or rectangular plan shaped buildings are more preferred as compared to complex geometry type of buildings, for example T shape or L shape. So during field visits, we have observed many buildings of dry stone construction are actually rectangular. However, we cannot ignore the possibility of irregular configuration even in the dry stone type of buildings, we have observed few buildings of irregular or complex shape such as T or L shape. So that you can see here in these two pictures, where I have put the figures corresponding to rectangular plan as well as T-shaped plan. Similarly, the other important characteristic of these buildings is that they have very small story height. You can see in this figure that there is only 1.4 meter height of the story used in this building, which is used for residential purpose in the near Shimla. So you can see that in general, these buildings are having very small story height, but few buildings can be of larger height as well. So here, the bottom building is representing a building height, story height of 3.2 meter. Similarly, if we see the openings, door and window openings, then we see that here, mostly the buildings have lesser opening, however, few buildings have larger opening. So what are the implications of openings? If a building is having lesser amount of opening, that means more area will be available to resist the shear forces that will be developed during seismic action. Therefore, larger the area, lesser will be the stress. So therefore, more will be the chances that the building will survive that earthquake. So we can see that there are many types possible in this dry stone construction in terms of wall openings, but most of those buildings are having very less opening ratios. Now coming to the next aspect, they have very large thickness. So therefore, during winter season and during summer, they are able to maintain the temperature differences inside and outside the house. So that is one of the characteristic advantage of this traditional type of buildings, because of use of very large thickness of the walls. So in some buildings, we have observed walls are as thick as 600 mm. Then you can see that because these buildings are found out in a region which is characterized by hilly terrain, so there can be different possibilities of existence of building with respect to the slope. For example, building can be located on a flat ground, which is shown here. Then you can have a building which is located on two foundation level, because here there is sudden change in slope and slope is going downward at this location. So there are two different elevations in this building. Here you can see that this building is following the natural slope of the ground, and here you can see that the ground level is very at the location of the building, ground level is at very low level. So an artificial platform is created to make or raise the ground level, and over and above that the building is constructed. So this type of building is called a building on artificial platform. So we can see a variety of combination in terms of structural configuration of buildings when we see it in hilly terrain. Now coming to the material that are used for their construction. So of course, one of the material we have seen, as the name itself suggests, is the stone. Then because in only few cases plastering material is used, so we can see that both type of plasters can be seen in the construction of these dry stone buildings. One is the mud plaster, the second one is the cement plaster. But cement plasters are used in very recent or modern construction of dry stone building, whereas in older construction only mud was used. Similarly, for flooring purpose, there can be a number of options. For example, plain cement concrete flooring, then you can see wooden flooring, and also you can have a reinforced concrete slab, and then there can be earthen cover over RCC. So these different types of flooring systems are used, and most of them are actually from the locally available materials, except the cement plaster and these reinforced concrete slabs. The most of these materials are coming from the locally available materials. Now let us try to look at from the perspective of roofing types, that what are their characteristics. So one of the most important characteristics of the roofing type is that in these regions sloping roof is preferred. Why it is so? Because these regions are characterized by very heavy rainfall during monsoons as well as very heavy snowfall during winters. So therefore, to allow to slide the snow cover easily, usually the sloping roofs are preferred. Now, even in category of sloping roofs, there are a variety of roofs that can be observed in this dry stone construction. So you can see here that the first roof type that we can observe is monoslope roof. The second roof type which we can observe is a gable roof. Then the third roof type which we can observe is a hipped roof. Then fourth roof type which we can observe is a cross hipped roof. Then we can have a flat roof with RC slab or flat roof over which an earthen cover is laid down. So there can be a variety of roofing system which we can also see in this dry stone construction. Now coming to the roof supporting system. So you can see that how different types of roof supporting systems are there in existence for this dry stone construction. So the important characteristic about the roof supporting system is that there is no connection between the wall and the roof supporting system. This is the main drawback feature of this dry stone building system. The roof system is directly placed over the wall without any positive connection between the wall and roofing system. So as an earthquake occurs, the building will start moving, and because of no connection available between the roof and the wall, the roof will fall easily down. So that is one of the most critical aspect of this dry stone building construction. Apart from these, the other things can be easily taken care of. So the most vulnerable element in this dry stone construction, which we found from the perspective of earthquake resistance, is the connection between the roof and the walls. So this is one of the important aspects that we need to keep in mind. Now coming to the foundation and what are the current trend that we will try to understand with respect to dry stone building. So sorry. So to construct the foundation, usually again the filled stones are used in this type of construction. So foundation are constructed using filled stones. So usually a strip footing is used in which the width of the footing is kept slightly higher than the thickness of the wall, and the depth of the footing is kept such that until the hard rock is encountered, because hard rock is easily available in the regions where these building typologies are prevalent or oftenly observed. So therefore these type of buildings are mostly situated on hard competent rock, so which is one of the favorable condition for their good seismic performance. Now coming to the practices which are adopted in these building types from the contemporary construction. So you can see in these figures that now people have started using a combination of the brick masonry in cement mortar with dry stone masonry. See, here you can see clearly that they have used combination of these two materials simultaneously. Then you can see an existing building having dry stone construction, and then a new construction made for the same by the same owner, and that is made up of contemporary counterparts, masonry in cement mortar. Then even within a same building, there is stone slate and hipped roof along with reinforced concrete slabs. So again, there are modern construction materials as well as the traditional construction materials. Both are being used simultaneously. So the main idea is that now people are moving from traditional construction practices to the contemporary counterparts. But is it worthy to move towards the contemporary counterpart? For some regions it may be worthy, but for some other regions it may not be worthy. Let us try to consider them from the point of view of seismic vulnerability. So that I will be correlating seismic vulnerability of dry stone buildings and other traditional construction type with conventional or contemporary reinforced concrete buildings. So that I will take up slightly later. So this is an overall view of dry stone building. So if we try to quantify their vulnerability qualitatively, so there are several parameters which are available in literature. So I have taken 12 parameters which are important to assess their vulnerability. So these parameters are that their structural configuration should be regular. There should be having a clear lateral load path. So during earthquake shaking, they are able to transfer load from one element to another, and finally to the foundation, and then from foundation to the ground. Similarly, are there redundancy available? If one of the wall fails during earthquake, then is there any alternate path available to distribute that load to other elements? And what are the proportion of the walls, connection details, openings? All those parameters are included in this list. And what are the observation which we made during field survey? Based on that, corresponding to each of these characteristics, we have assigned a tag. So red tag means the feature is leading to vulnerability, leading to increase in vulnerability of this building, whereas the green tag is showing that that particular feature is leading to reduction in the vulnerability of this building, or that is a favorable condition. So you can see here, out of 12, here we are having more or less 2 to 50% of the features are in the category of red tag in dry stone building. So this is very qualitative seismic vulnerability assessment. Quantitative seismic vulnerability assessment picture I will also show slightly later. Now let us try to understand the another type of traditional construction which is being practiced in the Himachal Pradesh. That buildings are called Thatra buildings. So first building which I talked about was a dry stone building in which stone was prevalently used. Now the Thatra building, a construction which differs from the dry stone buildings in the sense that here the prevalent construction material is wood rather than stone. So again, you can see that this Thatra construction practice is again prevalent in the Himachal Pradesh. In the Chamba district mainly we can find this Thatra type of buildings. So let us try to understand the same features of Thatra type of buildings also. So mostly again in case of Thatra building, it is observed that their plan shape are rectangular to square. However, the possibility of irregular plan shape we cannot ignore. Some people have created buildings with L or T shape plan as well. In many cases, we have also observed that earlier the building was of rectangular plan shape only, but because of they need to increase more area to the building and they cannot go in the upward direction, so they have extended in a direction perpendicular to it. So that's why finally building ended up with L or T shaped plan. So again we see their characteristic feature. So in this type of construction, this bottommost story is used for cattle or storage purpose. So these are the one of the salient feature of this Thatra type of buildings. So the lowermost story is kept for storage purpose or cattle purpose. You can see here that the amount of openings which are present in walls are very less usually. You can see here that very small size windows are provided in these wooden floors. So one of the characteristic feature of the Thatra buildings is that here it is just like behaving like a frame, because in frame we get resistance from beams and columns, and in Thatra building beams are basically wooden beams and columns are, these are the columns which I am showing here. So you can see that these are the wooden planks, and in between wooden planks the stones are filled. In local language, this type of columns are called thola. So this thola provides the resistance to the vertical loads, as well as the framing action provides the resistance to the lateral load which is expected during earthquake. Now coming to the structural configuration. So again, where these buildings are prevalent, there can be a variety of configuration of structures because of presence of mild to moderate or sometimes even steep slopes. So you can see that a building can be on flat ground, a building can be on sloping ground, there can be a foundation at 2 different levels, then building can be on artificial platform, as we discussed in case of the dry stone buildings. So similar kind of configuration we can also find in case of Thatra buildings. Again, if we see in Thatra buildings, lower portion of the building is usually constructed with the stones, and in upper portion what people do, they use they make use of wooden elements extensively. Why it is so? Because in earthquake, the inertia force is generated that is dependent on mass and acceleration. So to reduce the amount of force on a given structure, they need to somehow reduce the mass of the structure. So to reduce the mass of the structure, the bottom story is usually constructed with stone, and in upper stories, they usually use the wooden elements. So therefore, the mass of the structure gets significantly reduced, and which helps in resisting the earthquake forces. So you can see here, again, I have shown some photographs of thickness of wall, which we have measured. Again, very large, thick walls are used in this type of construction. And you can see here that the tholas have been provided here. So you can see in this Thatra construction, this is the thola coming from top to bottom. You can see here. And if we see the typical cross section of thola, so you can see here, we have shown some dimension here. So this is again a thola shown here. You can see that there are wooden planks which are applied in alternate course in the two perpendicular direction, and the space in between these wooden planks is filled with stones. So these are the locally available materials which are used to construct these type of buildings. So usually the dimension of a complete thola is 450 mm by 450 mm. So it is just like a square column, out of which the 150 mm is the width of this element, another 150 mm is width of this element, and in between 150 mm the stone is filled. So likewise the tholas are constructed. So there are two types of possibilities that we have observed while connecting the different elements together. So these elements, there can be grooves in between, or they can be connected through nails as well. So these two types of possibilities exist to connect the tholas and provide a composite action. Now coming to the connections. So usually the connection between thola and wall, there are very limited buildings which we have observed in which there was some connection between thola as well as walls. Usually walls and tholas are unconnected in this type of construction. So there is possibility of failure of stone walls in between the story height. So it can fail, or crack can develop in the stone masonry wall in this type of construction. If we come for the flooring types, then again, there are different types of floorings that can be available. So there can be post supporting beams or wooden flooring system, then plain cement concrete flooring, or there can be mud overlay over the wooden flooring system to prevent the ingress of moisture in the wood. So these all we have observed during field survey. Now let us see that in some cases there are certain special arrangements people have used very wisely. So what are those arrangements? That while constructing the walls using this type of construction, they have provided these diagonal braces. You can see here there are diagonal braces of wooden elements around the openings. So why it is they have used the diagonal braces? Because providing these wooden elements in form of diagonal braces arrests the crack propagation. So if any failure occurs in the wall at all, that will be localized or limited to that particular region only. It will not propagate throughout the wall. So this type of arrangement is called the strengthening of the opening, and it is prevalently used in one of the other form of traditional construction practice that is being followed in Jammu and Kashmir, and that is called Dhajji Diwari construction. So Dhajji Diwari construction extensively used cross bracing members in this wooden members in the construction. So again, if we see the roofing type, so not much variation as we have observed in case of dry stone building. We have found in case of Thatra building, there are gable roof, hipped roof, cross dip roof, and RC flat roof. Whereas in case of dry stone buildings, we have also seen the monoslope roofs. Those we have not seen in case of Thatra buildings. Similarly, if we can see the roof supporting system, so similar to Thatra buildings, there are purlins and A-shaped trusses, which forms mainly the roof supporting system. And in some cases, you can see that a very large wooden member is used centrally at the ridge to support this roofing system. So these are some of the prevalent characteristics of the Thatra building, which I have listed here and discussed. So there are again foundations usually made of the stones only in the Thatra building as well. So the construction procedure of the foundation is similar to what we have discussed in case of the dry stone building, where they usually kept the width of foundation slightly larger than the thickness of the wall and then try to construct foundation using filled stone. Now in this construction also, many practices from the contemporary construction can be seen. So if you see these figures, here they have provided tholas, and then here there are brick masonry in cement mortar. Similarly, here in the lower portion there is bands, wood bands and the stone masonry, and in upper portion along with tholas they have provided the brick masonry infills with cement mortar to act as an infill. Similarly, we can see the use of steel members in the roof section along with the thola. So people have started using a mixed type of construction as well, in which some practices are adopted from the traditional one and some practices are adopted from their contemporary counterparts. So this is also one of the things which we have observed during the field survey while conducting field survey in the Himachal Pradesh. So again, in the same manner, we have indicated the vulnerable elements and favorable elements or indicators for Thatra buildings. So out of 12 parameters, here we have identified the 4 parameters in the Thatra construction which aids to their vulnerability, whereas in case of dry stone buildings, there were 6 parameters which were aiding to the vulnerability of those buildings. So from qualitative method, we can just say that the dry stone buildings are more vulnerable as compared to the Thatra buildings, what we have observed. Now coming to the contemporary construction, let us try to see the contemporary construction. What type of construction exists and what is their vulnerability? So if we look at, we can see different type of construction made up of reinforced concrete, masonry in cement mortar or concrete blocks. So different types of construction are in existence in the different regions from Uttarakhand, Himachal Pradesh, Jammu Kashmir, and then Northeast as well. So these are the structures which are located on a flat ground. But it is not necessary always that because these regions are characterized by topographic features, so there can be different configuration of the building itself. So you can see here the photographs of mostly the photographs of the reinforced concrete buildings or some masonry buildings as well. There are 2-level foundation buildings, which we have also observed in case of our traditional buildings. Then this is the building which is following the natural slope of the ground. Then we have a building in which the setbacks are provided to improve its architectural appearance. These kind of buildings is also in existence. These two slopes are more or less parallel to each other. So this kind of observation also we made during field survey, and then variety of configuration we have observed during field survey. So here you can again see a sloping ground building because slope is in that direction. So this is also a sloping ground building. Now coming to other type of construction which we can observe. So you can see that here an artificial platform is created to make the ground flat, and over and above that building is constructed. Here you can see that here a retaining wall is constructed on the downhill side, and over and above the building is constructed. Similarly, here and here also the artificial platform is created to retain the soil on the downhill side, and the base is extended and support is provided by columns, and then over and above the building is constructed. Here we can see the building on stilts in which the lower stories are kept open. So there is no infill, or it is not used for any purpose. It is just used to provide or create a flat ground type of condition, and only in the above portion the buildings are constructed. So these type of buildings are called buildings on stilts. A similar example in which this story is open, only there is columns, and above that the building is constructed. So a variety of buildings we can found in these regions. So now question comes whether these buildings are safe enough from the perspective of earthquake resistance. So let us try to look the expected damage in traditional buildings versus contemporary buildings. So first I will discuss about the expected damage in dry stone buildings, then Thatra buildings, and then modern construction of RC buildings. So here I have used the fragility curves, as I discussed earlier, that the fragility curves are the curves which representing the probability of exceeding or reaching a damage as a function of severity of ground shaking. So severity of ground shaking, here we are representing on the horizontal axis. So one of the parameters to measure the severity of ground shaking is spectral acceleration. Another parameter is peak ground acceleration. So these two parameters are representing the severity of the ground shaking. On the y-axis, we are having the expected damage which we are getting. So if we try to convert these estimates in terms of damage, what we will get. So as we already know that, for example, if we are talking about Himachal Pradesh, so most of the Himachal Pradesh is in seismic zone 5. So that means in seismic zone 5, we expect a peak ground acceleration of 0.36 G. So corresponding to a peak ground acceleration of 0.36 G, we can expect, if we convert it into spectral acceleration at 0.3 second, it will be around 0.9 G. So let us try to compare that how much damage we are going to get if a building is located in seismic zone 5 and if it is of dry stone type. So these figures, the last one, correspond to the expected damage in seismic zone 5. What are these two different figures? The first figure is the analytical measure and the second figure is empirical measure. So what is the difference between analytical and empirical measure? So the analytical measure is that it is this kind of exercise is developed, this kind of plots are developed based on some numerical simulation studies. Whereas in empirical type of fragility curves, these curves are developed from the actual post-earthquake damage data. So empirical curves are developed from actual field data. So these are actually the more reliable one. So because of availability of dry stone, availability of the empirical fragility curves for dry stone buildings, we can make use of them for our comparison purpose. But it is not necessary that for all building types, empirical fragility curves will be available. That we will discuss just in the next slide. So if we try to see in seismic zone 5, we expect that if the maximum considered earthquake that we consider, or that is represented by a PGA of 0.36 G or spectral acceleration of 0.9 G that occurs in seismic zone 5, then among all the dry stone buildings, roughly 40% of the dry stone building will completely damaged. That means there are 40 buildings which will be damaged, completely destroyed if a maximum considered earthquake occurs, and those are made up of dry stone type. Same estimate we are also able to get from this empirical one. So because the empirical curves are assumed to be more reliable, therefore I have put the both analytical and empirical here. So you can see that the chances that the building will collapse if MC earthquake occurs in seismic zone 5 is 40% for dry stone buildings, whereas these chances reduce in zone 4 and it becomes approximately equal to 20%. So you can see here in zone 4, these chances are approximately equal to in between 15 to 20%. So in zone 4, the probability that the building will collapse or completely damaged if it is made up of dry stone is 20%, whereas in zone 5 it is 40%. Now let us try to look the Thatra construction. Of course, in case of Thatra construction, because we do not have any post-damage earthquake data available with us. So the only analytical fragility curves are available with us. We do not have any empirical fragility curve available with us. So if we try to compare their vulnerability, so we can see that as compared to 40% probability of collapse in zone 5 for dry stone building, the collapse probability of Thatra building, which we are grading in zone 5, is only 2%. And if we try to see in zone 4, it is even less than 1%. So we can see that the Thatra building, which are made up of traditional materials using wood and stones, are performing extremely well as compared to dry stone buildings alone. So this is one of the important aspects that I wanted to convey from these figures. Now let us try to compare the traditional construction with contemporary one. So here I have plotted 3 different types of damage estimates for reinforced concrete buildings. So as you may be aware, or maybe I will put a little introduction, that in reinforced concrete buildings, we are mainly relying on the ductility. If a structure has good enough ductility, then it will perform better as compared to a building which is non-ductile. But the problem is that in our construction practices, most of the buildings are non-engineered, and therefore the ductile detailing is completely not followed in their construction. As a result, those building falls under the category of non-ductile building. So a majority of buildings which are constructed in India are basically non-ductile. Those are not ductile one. What is expected, we should construct the ductile building, but actually we are constructing non-ductile building because most of the buildings are non-engineered one, and even if those are engineered one, the ductile detailing provisions are not followed in many of the construction. So if we compare the ductile building in seismic zone 5, you can see here the probability that the building will completely damaged in seismic zone 5 is again 40%. That is more or less equivalent to what we have got in case of dry stone buildings. And in zone 4, if we compare, it is around maybe 25%. So if we apply engineering to this building, then we can convert these buildings into ductile buildings by appropriately following the detailing guidelines given in the Indian standard. If we provide the ductile detailing again, then the probability of collapse of this RC construction is expected to be around maybe 8%, something like that. Here you can see that it is 92 to 100, so it will be around 8%. And in zone 4, it is around 1 or 2%. So again, you can compare these estimates with the Thatra building, which is a traditional building. So if we are making a RC building even ductile, its performance is going to be more or less comparable to what we are getting from the Thatra building, which is a traditional construction practice. So even with the engineering knowledge which is available with us, if we are making a ductile building of reinforced concrete type, then again the expected behavior in terms of or expected loss, we are not reducing losses to that significant extent when we are comparing it with the Thatra building. So this is one of the major thing which I would like to mark, that it is not always necessary that the modern construction practices are always better as compared to the traditional one, because we can see that the vulnerability estimates clearly shows us that the traditional construction practices have lesser chances of getting collapse or getting damage as compared to the modern construction practices in which we use the reinforced concrete building. So now naturally question comes, because we have already seen that in case of dry stone buildings, the damage is relatively larger because the probability of collapse is 40%. We cannot accept it at all. But in Thatra building, because the chances of collapse are very less, we can accept it. So now naturally question comes that what next we can do for increasing the safety of traditional buildings. So to increase the safety of traditional buildings, what we can do? So we can incorporate certain measures. For example, the walls can be secured through welded wire mesh. so that those wire mesh can be provided on both the faces of the walls, and then they can be connected so that wall will not fail in the out of plane action. Then we can provide seismic bends to reduce the vertical span of the wall, so that will prevent the failure of the wall. So to increase the safety of dry stone building, what we are trying to do here is, we are first trying to identify what are the potential failure mode of those dry stone buildings that we are trying to identify, and then we are trying to identify that what will be the possible measures that can avoid those potential failure mode which we expect in dry stone buildings. So these are the potential measures. If we incorporate in the dry stone building, then their failure or the probabilities can be reduced to a significant extent. So these are the examples just I have shown here. So wire mesh, use of bends. If the wood is available in scarcity, then instead of providing the double bend, we can have a single wooden bend, and then those can be connected like this. Then in the roofing system, because the cross bracings are not provided, so those are flexible in their own plane. So to improve their in-plane rigidity, we can provide the cross bracing in the roofing system, so that will increase their rigidity and prevent the failure of the roofing system. Then we can provide the appropriate connection between the bend which will be provided at the roof level and the roofing system. So those connection details are also shown here. So by using these appropriate measures, we can really improve the performance of traditional building, that is specifically the dry stone building, which we have observed to be more vulnerable. So these are some of the typical drawings which we have made for these two types of construction. So the first picture is what we have observed mostly during field surveys, and the second and third pictures are showing basically what is suggested, how to construct these type of buildings. So there can be two possibilities in dry stone construction, and there can be two possibilities in the Thatra construction as well. So one is that we need to reduce the vertical span of the wall. So we can provide the bends at the plinth level, sill level, lintel level, and roof level. So these bends will try to provide an integral block section of the building as a whole, as well as they will prevent the failure of the walls in the out of plane action. Similarly, these cross bracings in the roofing system will add to the in-plane rigidity of the roofing system. So therefore, the failure of these roofing system can also be prevented. So by incorporating these measures, we are trying to reduce the vulnerability of dry stone building. Similarly, if we can provide wire mesh in the dry stone building, then that can also help in preventing the out of plane failure of the walls. In case of Thatra buildings, one possibility is, if we want to reduce the mass at the top level, so that bottom story we construct using stone, upper story we can construct using wooden elements. Then if the span is larger, then instead of providing tholas at the ends, there can be a possibility of providing thola at intermediate level as well. So these kind of modifications we can make to these traditional building construction practices, and that can really help in reducing their vulnerability and achieving the goal of disaster risk reduction, because we have already seen that earthquake risk we can reduce by only reducing the seismic vulnerability of the housing stock that we have. So just to summarize what we have discussed in past 50 minutes, so construction practices and existing housing stock in Indian Himalayas, we have seen that those are significantly different from the structural and architectural consideration than those which are practiced in other parts of the India. Why it is so? Because of the two reasons. One is the unavailability of the flatland that leads to their configuration irregularities in terms of the building can be on slopy ground, building can have two foundation level, building can be created on an artificial platform. And the other consideration is that their openings and other parameters, story heights, those are relatively lesser as compared to what is observed in other parts of India, mainly because of their climatic condition in the region of their existence. Because of heavy rainfall, heavy snowfall, which kind of practices they have adopted traditionally. So there are several earthquake resilient features which we have observed in these type of buildings in terms of robustness of their structural configuration, mostly of square or rectangular shape, redundancy, that means there are more number of walls, more than 2 walls. So if one wall fails, the load can be transferred to the other wall. Then reduced seismic weights, specifically in the upper stories. So these are their characteristics feature which are earthquake resilient features. Then of course we know that both have their own advantage and disadvantage, but the traditional construction practice addresses the inaccessibility and socio-economic issues of communities, because a large part of the regions where these traditional buildings are constructed, those are located in a very remote areas, so they cannot use RC or other type of construction with that much liberty. So therefore these traditional buildings also addresses this inaccessibility and socio-economic issues of the communities. They also conserve the culture and provide a sustainable way of disaster risk reduction. So only the thing which we need to take care into account is that we need to consider adequate intervention, for example, which we have discussed in case of dry stone buildings, that how we can reduce their seismic vulnerability by incorporating certain measures. So this is the way which we could think of. Then because of the tree falling, now one of the major challenge why these people are forced towards the reinforced concrete or the masonry construction is that now government has banned tree falling, so there is scarcity of wood. So to replace the wooden elements in these type of construction, we need to investigate and identify the other alternative techniques of materials, so that we can promote these type of building type traditional building construction practices with the minimal effect on our climate. So this work which I have presented, this work was actually financially supported by National Disaster Management Authority, Ministry of Home Affairs, Government of India. Then the survey work which we have conducted was, I mean, a team of surveyors were there. So few of my PhD students and then lab assistant also helped me. So they are acknowledged, and this presentation was prepared by one of my research scholar. So again, his help is also gratefully acknowledged. And I would also like to thank Assam Downtown University for their invitation to present this work. So if you have any further information required on this aspect, please feel free to contact me.
Thank you, Dr. Surana. It was such a wonderful discussion on traditional construction practices, and I would request you to kindly give some more detailed discussion on traditional Assam type construction, because that is one of the very good construction practice for disaster resilient society.
So just to add,